Hello, everyone. Welcome to the webinar. We will begin in a few minutes. Please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 people in the room, please enter the number of attendees present in the questions box. Hello, everyone. Welcome to EPA's 17th Annual Drinking Water Workshop. We are glad you could be here virtually with us today for webinar training T3 on treatment and distribution system models. If you have not done so already, please take a moment to respond to the poll on your screen. How many individuals are attending this webinar at your location? If there are more than 5 people in the room, please enter the number of attendees present in the questions box. We'll hang on a few seconds for you guys to answer this poll. Now, let's hear from Tom Speth, who will introduce our first speaker and help moderate the webinar.
Great, thank you very much. Can you hear me, Gail?
Yes, we can hear you.
Okay, great. Well, welcome. This is a new thing we're trying by taking the annual Drinking Water Small Systems Workshop and making it virtual. So appreciate everybody dialing in, and please be patient with us because this is the first time we've taken this this type of thing to this scale. We've done Well, of course, we've done webinars for years, so we're familiar with that aspect of it, but we haven't taken an entire workshop virtual. So this week's going to be very busy, and I hope everything goes very smoothly because we're running around doing multiple things at multiple times. So bear with us if there are a little bit of technical difficulties. Again, thank you very much for attending the workshop. Today we're doing training sessions, and this is training session P3, which is the Treatment and Distribution System Models training. So we have a number of speakers lined up, and I'll shortly go over the agenda. But before I do that, the presentation slides, if you're interested in them, they're located in the handout section of the dialog box that pops up on your screen. So you can find the slides there if you want to peruse them yourself. Of course, they'll be displayed on the screen as we go through them. Also, if you've got a question during similar to the webinars, if you have a question for the speaker, please type that into the question box, which is on that same dialog dialog box. We'll organize the questions. Since there are over 600 people signed up for this training, we can't really do a one-on-one kind of questions during the talks. So we're going to have to kind of hopefully address them after the speaker. And I think we've allotted enough time after each speaker to go through some of the questions. And of course, we're available here at EPA in the future to help resolve issues if you have questions beyond this workshop or this session. Of course, technical issues, you can go to that link that's near the bottom of the screen, cadmusgroup.com address if you have technical issues with this presentation. And also note that we will be sending out attendance certificates after the workshop as we get everything sorted out from all the various sessions this week. So again, welcome. This is the EPA ASBA Small Systems workshop, virtual this year. And so next slide, please. So today we've got two different models that we want to cover, and they're different. They're very different. So we understand that one might appeal to you more than the other. But first will be what we call our ETDOT models, and these are freely available models used to predict the performance of water treatment processes. Today, we're specifically going to talk about the granular activated carbon models to remove contaminants such as PFAS and how those models can be used to optimize treatment and then the resulting cost at a particular system. And Johnathan Burkhardt will present that this morning. We're going to then take a break for those people on maybe East Coast time or Central, a lunch break. For those on the West Coast, maybe a brunch break. And then we're going to cover EPANET models. This is open source software, free, used around the world for modeling distribution systems for decades. And EPA offers this and continually encourages the development of this model through the years. And we have two speakers on that after the break. And so we'll cover both of these models today, and we should have you out in about 4 hours today. So next slide. Here's our disclaimer at EPA that we have on every presentation. Next slide, please, Jen. All right, here's our agenda. So I'm covering the overview right now. We're going to hand it off to Johnathan Burkhardt, who will talk about the drinking water treatment models, or the ETDOT model. Then we're going to handle questions for 20, 30 minutes or so, then take a break, come back at about 1 o'clock Eastern time, where Robert Janke is going to talk about the EPANET model, and then hand it off to Feng Shang later to talk about some of the application examples. And hopefully we'll have enough time for everybody's questions, and by 3 p.m. Eastern time, we'll wrap up. Next question, or slide. All right, we wanted to ask a couple questions for you, just to get a feel for where you're at. so these should go quickly. The first one is where you're employed, and just to get a feel from where you're coming from. And the next one will be specifically about how you use models. So take a few seconds to click on your answer here and send it in to us. It would very much appreciate to get a feel for where the audience is. Okay, I hope that was enough time. I don't have a clock that's ticking down, so I'm not sure. So the next question then will pop up shortly. Yeah, if you could answer this question too, and that'll help us kind of hopefully kind of work this training into where you're at. So take a little time and click on what's the appropriate experience you have. Okay, thank you. I hope everybody was on top of their computer and was able to very quick on the answers. I appreciate you answering those questions. And then the next slide is our first speaker. So let me introduce Johnathan, and then he'll take our presentation away, and we're right on time. So Johnathan Burkhardt is an environmental engineer with a BS, MS, and PhD in chemical engineering from the University of Cincinnati. He has focused his research on water treatment modeling of adsorption technologies, or these ETDOT ad designs models that he'll present today. He also works with water distribution system models, the EPANET models, and the detection and models for detecting contaminants and such, and monitoring applications such as the Canary model. So with that, I will hand the podium over to Johnathan Burkhardt, and he will take us through our first modeling training.
All right, thanks, Tom. Looks like from the poll, we have a lot of people who have not used or have very little experience with modeling, so hopefully we can help correct that after today. So as Tom mentioned, we're going to be focused on the ad design module within ETDOT. ETDOT has a number of other software packages within that, but we're focused on the GAC code today. And so today I'm just going to sort of talk through the slides very quickly and then transition to a live demo of you know, how to use it in actual time, just to walk through the examples. So that's what this is talking about. And then at the end, we're going to sort of talk about very briefly introducing some models that we've been working on that will sort of take the ad design modeling into the future. And, you know, we've transitioned them into Python, and this is still under development, but I'm going to highlight some of the capabilities of that for anybody that wants to, you know, continue on with the modeling in a different way. So a very high-level overview of the model is, you know, we can go from very simplistic, which is the green line here, which is the, you know, instantaneous kinetics model, and that is available in ad design, and it's under the equilibrium column model, or ECM. And we're not going to really focus on that today. When this was originally designed, ECM was the fast, quick model that would give you a pretty good estimate for where 50% breakthrough would occur. But now that computers have advanced, the pore and surface diffusion model, which is the black line in both of the curves here on the right, is we can run that in a matter of seconds. So on the top right here, we have a you know, simplified kinetics without a fouling. The lower right here, we have with fouling. And so ad design can model with or without fouling. And it does that by taking into account, these on the left here, sort of the simplified view of the model is a film transfer resistance or film transfer coefficient, a pore diffusion, and a surface diffusion. So we have a surface diffusion is along the surface of a pore. Pore diffusion is once it's broken through the film transfer, it actually can migrate through the pore. And then these multicolored dots sort of simulate what the fouling NOM, or it could also be just other materials if you're modeling a multi-species competitive model. As those adsorb onto the surface, you have those compete with each other. And so all of those things can be modeled in PSDM or the ad design model. So before we dig into that, I also thought it would be useful to highlight a few resources that EPA provides that have some of the values that the model uses, and we'll talk about how they're used. But CompTox is a resource, a database that has a lot of different information about things like molecular weight, molar volume, and other parameters, liquid density that the model uses. And so you have the link here that you can refer to as you need it in the future. Another resource is also the treatability database, which we have compiled lots of different sources, journal articles, things like that for treatment data. And so you can go to the link here, and the links are also repeated to the end of the slides. But this will just give you data for, not only GAC, but ion exchange, reverse osmosis, and just a good overview for treatment technologies. So that could be useful to you in the future. But one of the treatment technologies is specifically GAC isotherm data, and that would be directly related to these Feng-like isotherm parameters K and 1/N. And again, you can just search EPA TDB in Google and get that. So this is sort of a snapshot view of what you might see from the treatability database. So again, you can export this into Excel and look at it, not through the web as well, and save that for later. So for those of you who haven't already gone and searched for ETDOT, you can go and search EPA ETDOT, and you'll be taken to this website. And to get the actual software, it's under this Access ETDOT, the red circle here, and that will actually take you to the GitHub site. So last year, we went into an agreement with Michigan Tech, who originally designed ETDOT, to distribute this for use by the public. And so here's a list of all of the different models. Again, we're going to be focused on just the top one, this ad design, but it also has other modules for advanced oxidation, aeration, and so on and so forth. So once you get to GitHub, GitHub can be a little difficult to navigate, but they have this releases tab here on the right of the website, and you would just click on that, and then you'll be taken to another page, and you just want to follow this download the ETDOT_1-0, and that's actually the zipped version of the CD that was typically distributed if you've ever used it in the past. And so if you look at the installation instructions, you can see the big key here is this point number 4, and that's the license key that you'll need to actually install. And then another just tidbit is that for Windows 7 or newer, you'll have to go in and set up a compatibility mode for this, because the original code was designed 20 plus years ago, and so a lot of the things have changed in Windows. So you'll just have to go through and adjust the compatibility mode to actually run the software. If you install it, once it's installed, you'll just find it under ETDOT programs, and you'll notice that you'll have ad design, but you'll also have ad design manual. So the manual is very good, and give you a lot more detail. So I'm just going to be focused on the use of this, but the manual itself actually talks about, you know, some of the formulations and pulling that all together if you're interested in the formulas that went into developing the code. But if you click on Add Design, a screen that on the right here will pop up, and you'll just say Continue. And again, I've already got it running on my machine, but the next screen you'll see is the screen on the left, and this is just an example. We'll go through this in more detail. So the main screen for Add Design is divided into these 5 sections. So in the upper left, you have compound information, and that's where you would put the thing you're trying to remove from water. You have the column information in the upper right, and that's just the design specifications, the length, the diameter, and so on. The adsorbent information, and so this typically is carbon, but it doesn't have to be carbon. And that just defines a couple characteristics about the adsorbent. The lower left here is co-location. This is more for how the model is actually run. We'll talk about these numbers in a second. And then the duration. So how long do you actually want the simulation to be run for? So this, in this case, it's 174 days, and we'll walk through that in a second. And so again, this compound information, you can add and edit compounds that you want to model. You can add more than one, and you can, you know, run them competitively or in single situations. So if you would add a compound, another screen will pop up. It'll have these characteristics. Again, we'll walk through these in more detail as we go through, you know, running this simulation. But again, you have all these other bits of information. And the big one that's also important that sort of ties back in to the previous slide is these are the mass transfer coefficients that would define the limitations. So film, surface, and pore diffusion. The column information, again, we just want to supply the physical characteristics of either a pilot that you're trying to model, an EBCT, or I'm sorry, the RSSCT, the small scale columns, rapid small scale columns, or just a full scale contactor if you are trying to model full scale. And what you'll notice here, I'll just mention this, is that flow rate and EBCT, or empty bed contact time, are linked together. So if you know the empty bed contact time you want to model, you can type it in here and it will adjust the flow rate. If you know the flow rate, you can just verify that the empty bed contact time is what you expected. And again, the drop-down menus, which we'll talk about more here, will adjust the units, so you can use whatever units you prefer. And again, the adsorbent, we have more information here for, there are a few manufacturers. So if you actually open this adsorbent database, you can see some of the, there's a dozen or so, a couple dozen adsorbents that are already characterized. And then you can, it'll just pre-populate these, the density, the radius, and so on and so forth. But you can adjust those if either you want to model a ground carbon or just see what the effect of those would be. And so the co-location is going to talk about it's sort of the math. The big thing is if you get a lot of oscillations in your simulation, you can adjust these up. And so basically what happens is this simplifies the problem so that the computer can solve it efficiently, but sometimes it makes the wrong guess, and so what you'll get is sort of an oscillation in the resulting the breakthrough curve. And if you get that, then you can adjust these upward, and so you just need more points. And so there's not really a rule of thumb, but the simulation code will not allow you to make either one of these greater than 18. It's limited to that. But basically, I find that in a lot of cases, you know, 8 for radial and 12 for the axial is sufficient. And we'll talk about that as we go through a real simulation. And then again, the duration is pretty simplistic, but The big key here is it may yell at you, and I'll simulate that in a second. But basically, there's a limit of 400 time steps. So if you want to say, for example, simulate 1,000 days of total runtime, you would have to increase your time step to 2.5 days in order to, account for that 400. And so it'll just tell you that it can't allow that input. And so what I'll do is typically I will adjust the time step upward, say 5 days. I'll adjust my total runtime upwards, and then I'll go back and try to make a finer grid time step until it yells at me. Or you can just calculate it if it's an easy round number, for example, the 1,000 days. And so just again, this is more for your reference. We'll walk through it again. When you run a simulation, you just go to run. In this case, we're talking about pore and surface diffusion. And but you have these other two choices, and so that's the homogeneous continuous pore diffusion model. So it's very similar, but it's making a few other assumptions, or that equilibrium column model, or ECM. Really, I only use ECM or PSDM. The assumptions in the CPHSDM anymore, the simulation time for the PSDM is so fast, you don't really need this middle case. And so if you click run, a new dialog will pop up, and it'll say the calculation was started, it ended, and typically you're going to see some very small, few seconds simulation. And sometimes you will see an error. If there's a problem, you'll see an error here, but hopefully after this training, all the pitfalls will be avoided. So if you click on you've run the simulation, now you click on the run or pull up the results. In this case, there's a competitive 3-component system, and so you will get a window that pops up that'll look kind of like this. And in this case, you have the three species being modeled, and you have the colors here on the right of the figure. You can also adjust how you're plotting it. So in this case, it's time, bed volumes, or volumes treated per mass, and then you can also adjust the C over C naught, or you can just have the units, micrograms or milligrams, if you know that as well. And so if you just ran a single simulation, so again, you'll see that this is the only species that's being highlighted. And so it'll just run a single case, no fouling. And again, we'll talk about how you select fouling as well. But you'll see just one compound is plotted. You'll have the table here at the top that sort of 5% breakthrough, 50% breakthrough, and so on. And so it's, again, same process. You've run the simulation and just are viewing it. If you are interested in fouling, again, this is more for reference. We'll walk through it in more detail. But you will click on fouling under options. You'll get a screen here in the upper right. And you will have the type of water, and then you'll also have which chemical you want this to apply, and then what the type of correlation. And these two, again, are detailed in much more detail in the manual. And then there's also, a number of papers that have sort of highlighted the use of this as well. But the other thing that we'll have to go to do, and we'll walk through this, is you'll have to go back to the species that you're interested in, and you'll click this box under the kinetics tab that says use pore diffusion coefficient for tortuosity, which will then adjust that. And that's applying a time varying tortuosity in addition to the changes that are related to fouling for the upper right. So the upper right window defines sort of the major effects, and then the kinetics will just define the fact that there's secondary effects that happen over time as well. And so this is just demonstrating the change if you apply this fouling. And so if you recall, I'll just scroll back quickly, the original no fouling case was breaking through at 400 days. But if we look with fouling, it starts to break through at about 100 days. And so you can see that that's a fairly significant effect. So at this point, I'm going to pause and actually go through the live demo of a few different cases, and we'll just wrap this up before we talk about questions, and this will be the new models. So, okay, so hopefully you're still seeing my screen. Tom, can you confirm? Or somebody?
Yes, we can see your screen.
Okay, so this is the window. So I'm just going to start a new case, and this is what ad design would look like, on your machine if you don't have it running. And again, the layout is as I described, and so if we just go here and we add a compound. So that's the first step you have to do. So you have to have a compound that you are wanting to model. So this, the default in in ad design is it says new compound. I know that these parameters are for TCE or trichloroethylene, and so I'm just going to rename that TCE. But that's just, you can name it whatever you want. And again, you have the molar molecular weight, again, different units, molar volume. So what you'll notice is if there's already a value in this field and I change it, it will just recalculate that as well. So you want to make sure that the unit that you want is the first thing that you change, because otherwise the units will change on you. In this case, I'm going to adjust this down a little bit to 25 milligrams per liter. Again, boiling point and liquid density, solubility. So what I will say is that boiling point is nice to know. Ad design does not use that for liquid cases. So if you're trying to model liquid simulations, boiling point, solubility, vapor pressure are not used for water-based simulation. So if you want to model gas, the process is the same, but you will need those. And so really what you need on this screen is you need a molecular weight, a molar volume, an initial concentration, and a liquid density. The other species or the other values are nice to know, but are not critical for the model. And then the parameters down here in the Freundlich isotherm parameters are where you are going to, enter the capacity. And so this is where the treatability database or other journal articles or sources might provide that to you, or again, a pilot might provide you information about this as well. And so again, we have a few different unit systems. If you open that, and again, I apologize if it's a little small on your screen, but you have, milligrams per gram, millimolar per gram, micrograms per gram, or micromolar per gram, and any other unit system that you might find in the literature you'd have to convert. So those are the only ones that are by default available. And so the thing to remember here is if you need to change both of these because they, you're not considering TCE, what you want to do is you want to put in your 1/n first, because that's going to be what I'll just highlight is if I change this now, it will convert, it won't convert this other value. But if I change them in a different order, actually it did change it, I'm sorry. Of course it doesn't do it the time I want it to. But if I know that this is say 100, what you'll find is if you do change the Freundlich value, sometimes the K value will change. And again, I'm not sure why it didn't do it that time. Normally it does. But again, from this screen, you also would want to look at the kinetics. And so right now the default is to use the correlation values for these, and the the SPDFR, or the surface to pore diffusion flux ratio, which some publications will also provide. And that's just the relationship between the surface and pore is what it says. And so if I were to change this to 4 or 5, you'll notice that the surface value changes just slightly from 0.148 times 10 to the minus 9 to 1.85 times 10 to the minus 9. You can also select any of these that you want by just selecting the user input. So if you know or want to adjust that to see what the effect of that is, to, for example, test the uncertainty around that parameter, you can just at any time go and select the user input value and adjust this to whatever you want. And so if I just change this to 3.09, then if I run the simulation here, it will use this 3.09 times 10 to the minus 9 value. But again, for now, we're just going to leave everything as the default. And I click OK, and that saves everything. If you click cancel, it will prompt you to say, did you really mean that? And again, I'm just going to change this back to 98, which was what the original value was. So if you're running this, just going through an example run, you'll see the same values. You can also get to the Freund-like isotherm values by clicking on this tab, but I typically find that I don't need this because I can change the values on this main screen just the same. And at this stage, again, it'll say data's changed. If I were to click cancel, it will say, wait, the data's changed. Do you want to make any adjustments, or do you want to save that? But I'm going to just click OK here. And now you'll see that TCE is in this main screen. For right now, I'm going to leave everything the same. And so we can go again and just look at this and say, I really know this in feet. So I'm going to go and change all my units to English or American units, pounds of carbon. And again, so bed mass is the actual bed carbon. Flow rate, again, let's just select this to millions of gallons a day. But again, you can select gallons per day or gallons per minute. So, and then empty bed contact time would be minutes. So again, it's a little under 10-minute empty bed contact time. And for now, we're just going to leave this carbon information as it is because we're just considering that as known. And we're going to run, again, the default simulation of 174 days. So again, we're going to go here and we're just going to say run PSDM. And of course, that's on a different screen. But it does pop up two windows. It pops up a window with the status, and then it will run, excuse me, the this summary window that just says it is completed. So once that's done, we can go here and say results, and we can say it will pop up this window. And so again, we now have the this new window with all of the different values. So 5% breakthrough is occurring at about 42 days, 95% breakthrough is about 51 days. This volume to mass ratio, so the volume of water that is treated for the mass that you supplied for that bed is DTM. It's similar to the specific throughput. But all these characteristics are provided. And so again, we can say time, bed volumes. So we can see that it's occurring, this is at VVT, so 6,500 bed volumes for that 5% breakthrough. And we can also adjust the unit systems. So we want that to be milligrams per liter. So again, we can just adjust that as we want as well. And we can also just get an Excel screen, which now we can go here and we say under edit, we can say copy entire table to clipboard. And so that'll just do like a control all and then copy. And so you can then pull that into Excel and paste that and do whatever you want. And so you get the columns again, time in minutes, the bed volumes equivalent of that time, the usage rate for that time, and then also just the milligrams per liter, so the actual concentration through time. And so what you'll notice is that there's a few of these values are negative, and again, that's just sort of the nature of the solver. It sort of oscillates, but you can kind of ignore those negatives because they're not realistic. But the overall breakthrough curve is what you would expect, but you can see that there's maybe a little bit of a wiggle right here at about 40 days. So you can adjust that again. So if we close this, we can just resimulate. So if I just sort of increase my radial direction, I can increase my axial direction and rerun that. Which won't really change the results because again, this one's fairly stable. But again, we get the notification that it was finished, and we get the overall breakthrough. But in this case, that very small wiggle, which may not have even been appreciable on your screen, has disappeared. You still will get some very small negative numbers, but that's sort of what the co-location points are doing. And that's just, again, if the default values are working for you, then you really don't need to change. But if you do find that there's oscillations, or it fails to solve when you expect it to solve, then you'll want to adjust these co-location points.
Hey, Johnathan?
Yep.
Just quick, I know it's a little late, but just to clarify, is there a way to make these screens bigger with this model?
So right now, no, there's not. It's sort of unscaling, and so back when this was new, this was probably filling a screen, but with higher resolution monitors, it's small. So we do have plans to try to update this to Windows 7 and Windows 10 compatibility, and that's definitely an issue that we would be looking at. So thanks again, Tom, for reminding me about that. I can try adjusting my resolution, but I'm afraid that might mess something else up. So, so if we just, to demonstrate the error message that you might get if I were to select this at 1,000 days, which we know it's breaking through in about 42 days, but so you don't really need to see this, but you'll see an error that says the time step is too small and the maximum number of points. So again, to adjust that, I would go here and I would say, 2.5 days time step. And now if I select 1,000 days, it will allow me to do that, and I can run the simulation again, and it'll just run the whole time horizon for 1,000 days. For this simulation, it's not really relevant because the 174 days is perfectly good. But so if we want to say run this with 1/10 of the concentration, I can go in here and I can say, well, I'm going to go to 2.5 instead of 25 milligrams per liter. Again, clicking OK. I'm going to run that again, and we should expect the breakthrough to be pushed back. And so by going down 1/10, our breakthrough days are now 158 to that 5% instead of 42. And so you can see, you can play around with the concentrations at the influent. And so again, I'm going to just go here very quickly, and I'm going to change this to 10 because I want to show you how to adjust the influent concentrations. So if you're wanting to model a variable influent concentration, let's say there's seasonality to the values that you're trying to model or something similar, you can go in here and say influent concentrations. And then you would say at day 0, I have the 10. So it's very important to recognize that this is in TCE milligrams per liter. And so If I want to say day, let's say 100, it's 5, 200, it is 7.5, 300 is, let's say 10 again, and let's say it's just 10 through the whole simulation. We can just enter those in. Again, this could be for fitting a pilot or something similar, or just again, if you know there's seasonality to the value that you're trying to do, you say okay. And so now if I run this, again, I'm going to bring up this results very briefly. So you notice that it's sort of fully broken through at about 200, but in this new simulation, I've reduced the influent concentration for a period. So we would expect that that would potentially shift that curve backwards. And so if I run that again, I can see now the results are now a little different, right? So we now are adjusting, and it's dropped down during the period around 100 days where you had a low concentration, and so you get this much more variable concentration in the effluent. And so you can also do this again for fitting pilots. You can put in this effluent data. So again, if we just do here, what you'll notice here is this is now in relative concentration, or C over C naught. So our C naught was the 10 milligrams per liter, which is what we put in that initial properties field. So I want to just say that this is 0 because this is now the effluent concentration. So if I'm going to say, let's say 100 days, it was at 0.5, 200 days was maybe 0.75, and obviously we want these to line up, but this is just sort of an example. So you want to put this in relative time or relative concentrations to that C0 value, or the initial concentration of the influent, right? Not of the effluent. And so again, if we then now have to rerun this again, just to make sure all the changes are there. And now what we want to do is we want to actually say compare PSDM results to data. So that effluent data, or this effluent concentration, now becomes your data that you're plotting it against. And so what you're seeing here is you now have 3 plots, and I'm going to just do symbols, which doesn't help, so we'll change back to lines. But the blue line is the effluent concentration from the model, and the green line is the influent, and the red line is the effluent. And so you would just be able to, again, if you have more data points, you can you can compare that, and again, we can look at that in terms of concentration, and so again, you can kind of see the red effluent data. You would try to line that up. Again, hopefully you have enough time resolution to potentially capture this realistic change if it were to have occurred. So that's the simple single component view. And so the last thing that we would want to do is we want to look at fouling. And so that was assuming that there was pure organic free water or very low NOM water that would be experienced there. So if we go to options and we go to fouling, we would look here, and you have these organic free plus 5 other chemical type waters. And so the Rhine River is a surface water. There's a different surface water that I believe is a lake. And then a few different groundwaters with slightly different NOM or DOC values. And again, the manual will have those more data about those values. But in this case, what's that?
I hate to bust in again, but there's some questions about how you added TCE on that last step.
Added to this step?
Yeah. Yes.
So we would just click the add. What was that, Tom?
Yeah, that's right. Could you go over that one more time?
Okay. Yeah, so if we go to add a compound, we get this new window for the component properties, and I just typed in TCE here, and I'm just going to name it 1 just in case it yells at me. But again, you name your species, whatever you want. I mean, obviously it's corresponding to the parameters you're putting in, but then you would populate, these other values. So let's just say, I'm just going to say, made up. And I'm just going to change some of these just to walk through the example. So if I say that the molecular weight's 200, my molar volume, let's say, is 125. And then again, we'll leave the concentration there. And then the density would be 1.63. So again, I'm just making these up. Obviously, you would, have values for these. And then, like I said, these are the only, the molecular weight, the volume, the concentration, and the liquid density are the only things that the liquid phase GAC model, needs. And then again, we'll just, put in a lower value for Freund-like isotherm. We'll actually just change our unit system to the micrograms. So let's just reduce this down to 50 micrograms per gram. And we'll just leave the Freund-like isotherm at 0.43. And so again, once I click OK, at this point, it's not added to the add design model yet. So once I add or click OK, now you'll see that I have 2 different species here. So I have the TCE, which I was working with before, and then now this made up value. And so if I click on it when there's no coloring, I get a blue, and if I click on it again, I deselect it. So you don't, there's no shift or control, you just click on this. And so if I then click both of these, it will bring up a, it might not let me run it because I haven't put influent concentrations in for the made up species. So we'll see. This is a learning experience for me. Evidently, it just takes that as a. So I'm going to bring this other screen here. So this is the other screen that was going so fast that it was barely visible before. So this is clearly not wanting to run because it shouldn't be taking this long. So what we're going to do is we're going to increase the axial elements up to 2, and so that's just going to assume that there's a longer column with these other co-locations. And so if you need more than 18 axial points because the simulation is still not converging or it's taking a long time to simulate, what you can do is you can add another axial element or more, and it'll actually then try to fix the stability issues that's causing the runtime. And so if we run this again, that's going much quicker. Again, unfortunately, it's on a different screen. So it already got further. And okay, so then it finished. So what we can then do is we can look at the results, and I'll go through an example that will run faster there. But again, so in this case, the made up value, the made up compound that I added, the Freund K was so much lower than TCE that it just hasn't even broken through. So I'm sorry that I said that backwards, but actually I'm not sure why this is. Yeah, so this is actually a good example. So something was happening here. And again, it's very difficult even on my screen to see it, and I apologize. But you'll see that if you were to run the same thing, there's a lot of instability. There's this it basically gives up. And so because the formula K was lower, we would actually expect that to have broken through sooner because there shouldn't have been that capacity for this made up compound. And so basically, if I see this, something were to, should not have happened this way. And so we can try increasing the axial element again and see if that will solve my problem. Again, it ran, and so we can say, and it didn't solve my problem. Well, that's the problem with changing your script in the mid process. So we'll show an example where this actually does work in a second. So, but you can see that there's some cases where ad design does some things that you're not 100% sure about. And again, if you run something and you run into a case where your knowledge about the problem says that something should have broken through and it didn't in the model, shoot me an email. My email's at the end of the slides. I might be able to help figure out what the problem with the code is, because again, a lot of that will just affect or be related to these co-location points, and that is sort of a deeper dive than we really need to get into right now. But if we just turn off this made up compound, we go back to the single compound case, and so we'll go back and rerun that, and so we can see that it removes the if we go back to results, it removes that other made up compound that we saw. And we're going to go back to the fouling case, which is where I was before the question. But we want to go to fouling. And again, so this case, I'm just going to say Rhine River, and I'm going to see that I want to apply halogenated alkane, which is the species that I believe fits the TCE case. Again, this is not necessarily how you would do it, but there's the predefined cases here for pesticides, PNA, acids, chlorinated hydrocarbons, nitro compounds, aromatics, trihalomethanes. So really in this case, we could even select the chlorinated hydrocarbon, and so that's going to be a slightly different case. But if you want to go into an even deeper dive, either of these buttons will bring up another dialog, and these are the actual parameters that the manual will talk about, how they were developed, and there's one or two papers that talk about them as well. And so I didn't actually make a change, but it'll ask me, are you sure? And I will say, I am sure that I don't want to save it. Otherwise, you can save a new value. So you can add a new water if you find that the 5 values that are there don't work. And then you can do a similar thing for the water fouling compounds. And again, this is a little outside of the scope of this talk, but if you're really interested in that, follow up with me afterwards, and we might be able to correspond via email or call or something. And so again, it'll prompt you to say, do you want to save, or do you not want to save? And I say yes. So again, we'll go back and we'll look at chlorinated hydrocarbons. We'll select the value here. And if you recall from the previous slides, we'll have to go back in here and say, change the kinetics. So I have to go back into edit properties. Again, I'm selecting the TCE. But again, now that I have 2 compounds, I have a new dialog box here at the top of this component screen. So I can just select compound TCE. I can go to this kinetic screen, and I want to use my pore diffusion correlation. So I need to click this box as well. And I say OK, and I say OK again, and now I'm back to the main screen here. And again, we know that this was already working fine in a few 100 days. So I'm just going to reduce this down to 100 days. And I'm actually, didn't like that, 171. Just go down here, and I think 0.4 days should work, 0.45 days should work. So this just gives me a way to, because I know that the fouling should reduce my capacity, which means my breakthrough should be occurring sooner, then I know that I don't need that 1,000 days for this simulation. So I can rerun my simulation, and we can then go here, and I can go to run the fouling code, and so now I can see that my curve is occurring in a slightly different way. The one thing about the fouling code is it will only simulate to C/C naught of 1. So if you were to try to simulate something that, let's say, has some kind of overshoot in the case of the effluent, then this will just stop on the pre-breakthrough period or pre-overshoot period, and so this time horizon will only go out so far. And again, it's just sort of a tidbit to remember in the future if you use this. And in this case, this is actually only being projected out to the 174 days, so it's not being truncated by the C/C naught case. But again, that's getting a little deep into this, but it's just something to think about as if you play around with it yourself. So that's sort of the high level view. I guess I didn't dive into the adsorbent database, so I should do that. And if we click on that button, we'll get the new window here. And we have a few different cases, the Adochem, the Barnaby, Shootcliff, Calgon, Mitsubishi. So if we click on Calgon, we've got a few different options. So the values that are already available in this the database for this software are just are what you see. And again, you'll see these are available for liquid phase, and there's also some gas phase, which we're not really talking about today. But again, I was starting on the F400, so I can start there. And then I can say use these adsorbent specifications. And so again, that didn't change anything, but if I had selected a different adsorbent, it would have. But these are the main parameters here on this main screen that you're going to be using for the liquid phase adsorbents. And so we can just rerun that very quickly and remind ourselves what this looked like. So this didn't change anything. But if I make the bed longer, for example, I would say, let's say 12 feet, that's going to do two things. It's going to I'm going to leave the bed mass the same, which I would really want to increase that. Let's see if this, so I put a little bit more carbon because the bed got deeper. In reality, I would go through and calculate what my apparent density was, or I would know that from a real life contactor that you're trying to model. But I increased the EBCT for that system. So I'm going to rerun this, and we would expect this to now have a more prolonged bed life. So if we remember, it was breaking through at about 50 days. It's a little further back, so that didn't really change all that much. In this case, partly that could be because I'm not loading the full capacity of the carbon, so I might have additional capacity for carbon. So you can see you can play around with a lot of these variables, to either because you're in the design phase of a system, or you're just trying to see what the uncertainty of those parameters are. So with the installation, you also will get an example file, the liquid.dat. So if you actually, I just want the file open, and so it says, do you want to save this? For the moment, I'm not going to save that, but it will then open the liquid.dat example, which is, this is just in the original install folder. And I say liquid.dat. And then this will now have these 3 compounds. And I just wanted to show you what a competitive 3-component system would be. So again, this already came preloaded, but you would just go through the same steps of adding these. So if I go to the edit properties, again, trichloroethylene, I have the parameters. I can look at the tetrachloroethylene. Again, the parameters, you see all these are now different and they match the compound. And then toluene and all the parameters that go with that. And this comes pre-configured with the kinetics as well. And so you'll have to, if you need to change the kinetics of each of them, you'll have to adjust through the drop-down menu here. For now, I didn't change anything, so I'm just going to say OK. And I've selected all of these blue, and I can just say run these, and it solves that. And then if I pull this up, again, apologize for the color contrast, but this is now showing you that the tetrachloroethylene is breaking through at about 250, 300 days. I'm sorry, the trichloroethylene, the tetrachloroethylene is breaking through about 500 days, and then the toluene is still starting to break through, even at about 600 days. And so again, this is simulating out at 1,000 days. You could extend this further if you're particularly interested in toluene. And again, when you do this, you can see that I can get the Excel. And in this case, if I open the Excel, I get the 3 columns for each of the species that I'm modeling. And again, if I adjust this drop down here, I can look at the tables and then see, you can see that, they all change according to what the model is predicting. So that's really the main, run throughs, and I realized I kind of went through at warp speed, but we hopefully can address some questions. I'm going to leave this up in case we have questions for that, but let me go back and bring up the last few slides. Apologize. Okay. So again, I just wanted to touch on some of the models that we're working on to try to, make this a little easier, because obviously the ad design software is very easy, but it's sort of single simulation at a time, and it can be a little bit cumbersome to try to do data fitting from pilots, or even just looking at things like specific throughput and under variable conditions, or trying to treat to some kind of treatment threshold. So if you were to go to the link at the bottom of the page here, which is a different GitHub repository, you can download by using the clone button. And so this is it's Python. It's a little bit more of an advanced tool at this phase. We are still in the development phase for what this can do. So, this could be as powerful or more powerful than ad design. But right now, this is really set up to be used in conjunction with, just somebody that's looking to develop Python scripts to do more advanced types of simulations. So if you were to download clone, and you'll get this option to download the zip, and then this will allow you to copy or create a folder on your machine that will give you these files. And so you'll get this folder, and this is under the PSDM model. Under the main folder, there was an ion exchange model that's also under development. So if you're also interested in modeling ion exchange, we're working on that as well. But what you'll see here is there's 3 example files that end with .py and corresponding .xlsx files. And so what we've done is we're trying to move the input files into Excel, so you can, just have a list of Excel files that you can play with and adjust for different projects or different objectives. And again, the corresponding Python file that would go with that. So in this case, the top two have corresponding Excel files, and the example isotherm is still in development and doesn't have an Excel input file. But again, that's ongoing. So if you were to run the two example files, these top two, example_multi and example_TCE, you'll get these plots. And so this sort of runs through the exact same kind of thing that we've already talked about today. So in the upper left here, we have just the single compound, and that's analogous to what we've already talked about. Here in the middle, in the upper middle, we have a variable influent. So again, the input file sort of outlines how you would do that. And this also highlights the impact directly of fouling versus no fouling. And so you can see that within Python, we can plot multiple cases at once. In the lower left, we have the impact of the changing empty bed contact time. So I just reduced the empty bed contact time by 50%. But you can see that the longer empty bed contact time has a longer breakthrough, as we would expect. And the lower middle, we have a fitting algorithm, and this would be for if you have pilot data. So you now have green dots, and you have a dashed orange line. And then in this case, we have the best fit and the original true case, and they basically overlap. The parameter values are slightly different, and again, that would be captured sort of in the uncertainty case. So on the right here, we have the same thing that I just showed you, which is the 3 compound case. But what the new code, what we realized is that we could actually model the fouling and unfouled case, which the original code will only allow you to consider one species that is fouled with, and all the multi-component would then adjust according to that. Now we can model all of the species at once with a fouling related to NOM. So that is new. And again, as we work through the ad design upgrade, we will also consider, we'll see if we can make that retroactively into the old ad design functionality. And again, this is just sort of a bigger view of the fitting. So we can allow for predicting other different scenarios. And as I said, it's really just whatever you can think of, you can probably, if it can be modeled, you can include that and compare it and contrast. And again, export to Excel. So again, this is just the other suites. We also have a cost model that I didn't mention before, but that would be related to taking the performance modeling data and translating it to the cost model. So the Office of Water is managing their cost models, and they have cost models for a variety of different technologies and different things like that. And then we were talking about the performance model today, and then I already mentioned the treatability database. Again, more useful links, again, just for your reference later. And now we have potentially some questions for the audience.
Yeah, so we, can you hear me, Johnathan?
I can, yes.
Yeah, so we thought we could ask the audience some questions to see how well we were doing in terms of the class. So if you could take a few seconds here, and so the first question is, can the ad designs model simulate the impact of NOM following? And then in the answers, you can see which models do that. So if you could take a few seconds, and I don't know, Johnathan, you want to read through the questions and kind of walk through this? Or can you see it on your screen as easily as I can?
I can see it on the screen, so I'll just let the, it's one at a time, right? So.
Correct, yeah.
Looks like we're about 30% voted for this one. So evidently I did, I don't want to ruin the answer for this one, but it looks like it's yes in all three models. The answer is in fact C, not that I want to throw off the poll. And so PSDM is the only one that will actually model that case. I realize in the previous figure we did show that ECM had an impact on fouling, and that was sort of just a manual calculation. So if we go to the second question, or the, I guess, fourth question in the poll. So can ad design S model variable feed concentration? Well, it looks like we've got about half the people having voted. So again, it looks like I did another error for capturing this one. And so the variable feed concentration is only available in PSDM. So the answer is again C. So if we go to question 5. Can ad design model both gel type and macroporous? So I'm going to just not even, I'm just going to acknowledge I didn't mention this. So this is entirely my fault. And so the answer for this one is, it is C again, and it's just for the macroporous resin. So gel type is a different type of process, and that's part of the reason why we are developing the new ad design, or I'm sorry, the new ion exchange models to better capture, gel type and potentially a better interpretation of macroporous resin. So the next one. Does ad design provide goodness of fit statistics if effluent concentrations are provided? All right, so I think we've got a good quorum there for, it is both B and C. And so you can export it to Excel and perform the statistics in Excel, or the Python-based tool was developed with fitting in mind. So I think do I have one more? Can ad design simulate multiple components? So I think we've reached the capacity for this one. The answer for that one is A, correct, Tom?
Actually, this is a trick one, right? Because we didn't cover the CPHSDM too much, which is only a single component model.
Right, so it is B. Yeah,
so it is B. So it's kind of a trick question because we didn't cover the CPHSDM today.
Right. Yeah, so, and I don't use it enough to remember off the top of my head. So apologize for that one. But yeah, so I did mention it was limited in its assumptions. So, and then
I think we have one more.
Yeah, one more. Yeah. All right, so in the interest of time, I'm just going to call this one, and the answer is B and C. So you select the contaminant type and water type for this one. So I think we have a few minutes for a break. I'm happy to stay a little longer into the lunch break if people have questions, but I will definitely.
Yeah, we have a few questions if you don't mind, Johnathan. And the original schedule had us going to 12:30 until a break, so we have a few questions to roll through that people have sent in. So let me ask them. So there are a couple questions about what kind of formats or platforms these models can be run on. So can they be run on Apple or Linux, and is that in the future?
So the ad design model is Windows. The other model that I just highlighted at the end is Python. So Windows, Mac, Linux, as long as there's a Python interpreter, you can run it.
Okay. So when would somebody use the CPHSDM? Is there does it make sense at all these days to run the CPHSDM?
Tom, you might be a better person to answer for that, but as I said, I don't really use it because the PSDM is so fast. So it captures more of the features that I'm interested in modeling. So I don't know, Tom, if you want to expand on that, but for me, it's not. I don't use it. So.
Yeah, that's a good question because the only, and if you wanted to do something really, really fast to get a feel for when it breaks through, you might just use the ECM, which has only like 4 input parameters or 5, something like that. The only thing I could sense it used for is maybe if you're in a really big hurry and you don't want to deal with if you're not comfortable with setting the PSDM up in terms of clicking on things, that maybe it's just a little simpler to run it. And if you're dealing with a single solute and want to get a feel for kinetics, maybe it would be useful. But by the time you get it up and running, I agree. I think the PSDM, once you get familiar with the PSDM, you can usually just accept the defaults for the PSDM and just run that. So I'd probably say there's not much of a sense for it anymore, but somebody might have an idea. Okay, here's another question. let's see, what is a good resource for the component properties? Where would you go to get those other than what's in the model in terms of the database?
I highlighted CompTox. CompTox has a lot of the molecular weight, the molar volume, the density, and I didn't dig into that, but it does have both experimental and simulated values for that, so you kind of get a see the range. It can be as simple as Wikipedia. You can Google compound name and then molecular weight, and it might bring up a Wikipedia. For the inlet K and 1/n values, that's going to be the treatability database, journal articles. It could be if you're using the fitting algorithms, you could be developing that from a pilot study, or again isotherm studies for those kind of values. And again, I think for the diffusion coefficients, that could be the Handbook of Chemistry and Physics, or Perry's handbook, or something. But again, online resources, Novell. I mean, journal articles. It can be whatever. The sky's the limit, but those are a couple of the better ones.
Okay, great. Here's one. What have you done with modeling PFAS recently with these models? How have you used these models for PFAS?
Yeah, so we are in the process of looking at piloting data with PFAS, and so we have a few different things that we're hoping to get published shortly that sort of talk about the outline of what we did, and converting from the pilot data into full-scale modeling, and so again developing the parameters all the way to predicting costing and predicting the expected breakthrough intervals, like how frequently you would be changing out carbon in multi-bed contactors and things like that. So I don't know, Tom, if you want to expand on that, or.
Yeah, so I think that kind of covers it in a kind of a synopsis. So I think we've used it in a few real-world situations to get a utility, a feel for how long the beds would last, and particularly like the reactivation or replacement frequency and how big the columns should be for optimal design. So just optimizing design, optimizing the operation in general, I think is how we used it. How do they have to regenerate every 3 months, every 2 months, every 6 months? And looking at we did a lot, Johnathan, didn't we, on looking at different treatment goals in terms of if you change your treatment goal in the future, how does it change your design or operation? And so one of the rubs with PFAS is that some states have regulations, but more may be coming. It depends on what your state is. And so if your treatment goals change in the future, or if your influent values change in the future, what does that mean with regard to the design? And you want to set up a design that's most flexible, I guess. Is that kind of a good summary, Johnathan?
I appreciate you reminding me, bringing back up the varying treatment goal. That's an important aspect. I think you're muted.
Sorry. I've done this before. Anyway, what's the drawback for maximizing collocation points just in the beginning? Just maximizing them out.
Anymore for ad design, probably very little. I mean, I think that you could sort of miss like if you just go 18-18, you could probably sort of cause some problems on the other side. I typically haven't seen that, and so yeah, I mean, anymore, even with 18-18, the simulation time is under a few seconds. I mean, certainly under a minute. So you definitely could do that and say, set it and forget it. That could definitely be an option for a lot of systems. Muted.
What about adding adsorbents? Say you got a different adsorbent or a new adsorbent. How do you add the adsorbent? How do you punch in the K and 1 over N? How do you just briefly determine K and 1 over N?
Well, I mean, ideally, you're going to be doing an isotherm study, which is, you would fit the, you have the concentration at equilibrium against the capacity at equilibrium. So you would run a bottle test or other kind of test that would create a curve that says, okay, if my equilibrium concentration, which we consider sort of to be your supplied concentration, you would fit that to the data. So it'd be a non-linear fit. For fitting within the model sort of takes care of that. So you would provide it with influent data and effluent data, and then it does, like within the new tool, it will back fit those values. So basically, if you're looking at data and your breakthrough is after your actual breakthrough, your capacity is less, so you would reduce your K, or you'd modify your 1 over N. Your 1 over N might, that gets too technical. If you really have a question, specifically, maybe reach out, and I'd happy to give like an hour-long discussion about it. But for now, I think it might be outside of the scope. But
you can add in a new adsorbent that's not in the database.
Exactly. Yeah. And that's just the button, and then you'd add a database or add a value.
Okay. What if you're interested in just modeling something like TOC, which is which is a group of heterogeneous compounds in the water. Say you're interested in looking at disinfection byproduct precursor removal, and you wanted to model TOC breakthrough. How would you approach that?
Yeah, so I think you'd definitely be wanting the pilot data, and you'd want to be more looking at it from the backfitting from pilot data against sort of that the conglomerate of TOC in your system, and so the new tool probably would be a good fit for that kind of application. I don't know, Tom, do you have any specifics more on that, or?
Yeah, I think there are some more simplified models that can be done that have been developed over the decades that are more just more empirical type of fits that are not mechanistic in nature. But then there has been some work in the past of dealing with hypothetical components, whether it be one, where you're just making up a K and 1 over N in molecular weight for TOC, and then trying to fit the curve that way, and hoping that then other runs would be appropriate. And in the way gone many decades ago, there was efforts to use like 5 different components, and kind of creating a distribution of K 1 over N in kinetics, trying to fit TOC breakthrough profiles. It's not an easy thing to do, and I don't think there's any perfect answer. And it's very source water dependent. So some waters seem to be more easily modeled than others. In terms of, the trick is also that TOC changes with season, and so you can fit a breakthrough profile in the pilot data, but then what do you do to confirm that your fit can be run under different conditions and still be appropriate? So it's very hard to get both the training set and the verification set at the same time. Anyway, I hope I didn't go on a little bit there. Here's a couple quick questions at the end, and then we'll break. Can this be used for monochloramine reduction, such as what you might want to do for dialysis applications? Can you model monochloramine? Or Well, chlorine is very simple, but can you model monochloramine reduction on activated carbon?
So I haven't thought of that. I think that would, you know, if you're as it is now, maybe not. I mean, removal, yes, if you're talking about the actual chemical change at the surface, and no, right? Tom, that sounds right.
Yeah, these models aren't set up per se for that, but there's some other applications out there.
Yeah.
And I know some people have worked on that. And finally, I think our last question, what would you do if you had kind of a two thing? If you had a dual layer media bed, how would you handle the modeling?
Yeah, so that's something that we've looked at with like lead lag. And, you know, so what you can do is you can just say, you know, model the first step and then model the second step. And so you would feed the effluent from that first phase to the second phase. And so that is in development. And if you have specific, you know, needs for that, you know, reach out to me and we can, you know, try to use that as a demonstration case. But we have modeled lead lag. I didn't get into that. And, you know, some other cases, you know, similar to that. And that could even be, well, what if you have GAC feeding an ion exchange column? And so it would be, you know, you would model the first phase and then you'd model the second phase, because you can sort of assume that they're just in line with each other.
Okay. Let's see. In fact, okay. Can I use this model on the impact of a contaminant spill on the overall impact to the treatment of TOC removal? So can you use it both with contaminants and TOC at the same time?
Yeah, so I think if you've gone through the trouble of fitting your TOC model and you have a fairly good feel for that, then you would treat that as one component, you know, and that would be sort of the multi-species bubble. And then you'd have your other species, you know, say benzene or toluene or something that may be in a spill, and you're modeling that. So you would just treat those as a two-component or multi-component system where the TOC was one of those species. So that it could be done, right? But
yeah, I think it might be more of an impact on the effect of TOC on the contaminant more than vice versa, right?
Yeah.
The contaminant is probably not at a concentration that would affect TOC breakthrough profile.
Right.
Wouldn't you agree, Johnathan?
Yeah, no, yeah, it would just be the overall system impact. So yeah, you'd probably be looking at the other components breakthrough as your critical breakthrough, but yeah, so you're right.
Okay, and this model can handle other emerging contaminants like NDMA or 1,4-dioxane and things along those lines?
Yeah, so it as long as you've got the parameters, you know, to put into it, it's you know, and you can assume that the mass transfer limitations are the same. Yes, you just need the parameters.
Okay, and one last question, and I think we can, this is actually the last question we have. Does the program consider temperature dependency on vapor pressure for a compound? Now that would be for gas phase adsorption, but are you familiar with that, Johnathan?
So I'm less familiar with the gas. What you can put in temperature, and temperature is going to more define in the liquid phase your viscosity and your density of the water as your main carrier phase. But in terms of the temperature dependence on vapor pressure, I don't know that it does that, but I don't do the gas side of it as much.
Yeah, I'd agree with you. I used to do that many decades ago, but I can't remember how the model handles it in terms of, I think when you define your temperature, I think it does then give you your vapor pressure at a different temperature. But again, it's been a long time. Okay, well that finishes our questions. And we're right about on time. So let's take our 30-minute break, and we'll reconvene at about, we'll give you that 30 minutes, so we'll reconvene at 1:05 Eastern time, which is, so that's I guess for the East Coast people, that's a good lunch break. For the Mountain and West Coast people, maybe you guys can go to brunch. Appreciate you coming. So 1 o'clock Eastern time, 1:05, I'm sorry, 1:05 Eastern time, we'll reconvene. And thanks for attending our webinar. Hope to see you at 1 o'clock. Bye-bye.
Mhm.
Okay, Rob, are you there?
I am.
Okay, great. Let's get going again. I hope everybody's made it back. It looks like we have a large number of people still on, so that's great, over 400. So we'll be starting our afternoon session right now. Again, you can find the presentation slides under the handout section of the dialog box that is shown on the somewhere on your screen, and so you can access those. Also, if you have a question for Rob or Feng this afternoon, like we did with Johnathan Burkhardt, type it into the question box in that dialogue section, and we'll get to it after their talks. And we'll answer a few questions after Rob's, but we might save the majority of the questions for after Feng's talk so that they both can answer them together. And so we don't answer questions that Feng will answer with his talk. Again, if you have technical questions, you can get a hold of the Cadmus group on that link there that you see toward the bottom, and we'll be giving out attendance certificates. But it might take us a little while, just because we have a whole week of talks to go through. So it's going to be a little bit hectic this week. Okay, so if you advance to the next slide, we've got, we're going to be covering the EPA-NET models this afternoon. So this morning we covered the ETDOT, but this afternoon we're covering the EPA-NET, which are models to model the water distribution system, and for many different types of applications. And Rob and Feng will go over those this afternoon. And this is an open source project for this for these sets of software. So I hope you find it very interesting. Next slide, please. This is our EPA disclaimer that we have to have on every presentation. And the next one, here's the agenda. So we're starting out a bit late, but I think we're in good time. And if so, Rob Janke is going to start, and then Feng is going to take on after that at about 2 o'clock, and we'll wrap up at about 3 o'clock this afternoon Eastern time. Next slide, please. Okay, so we're going to ask a question here like we did in the morning. We realize that the audience may have changed a little bit from morning to afternoon. So if, so Galen, if you could throw up the first question that we have for the audience, that would be great. I think it's question 10, I think. Here we go. If you could just take a few seconds and plug that in, that would be great. Okay, good. I see that I can see that over half people voted. A little different skew this afternoon. A little bit more consulting people, perhaps a quarter of the attendees. But states are again the largest component of our audience today. So that's great. Welcome to all. Okay, our next question then. And a little bit of a question about, have you used distribution system models in the past? Give Rob and Feng an idea of, you know, where their audience is at. Okay, about 60% have chimed in. That's great. So a large percentage have not used distribution systems in the past, perhaps 2/3. But there's a sizable component that have either run EPA-NET in the past or some other distribution system model, perhaps the remaining third. So there is a component that have run these models in the past. So these are the results. So a little bit more, I think this morning we had a few more that hadn't run the modeling software in the past, and this is a little bit more skewed toward people who have experience, but still the majority of people, vast majority of the people have not run models in the past. So, okay, great. So let's go to our next slide. Okay, I'll introduce Rob, and I'm going to introduce Feng at the same time because, and then we can just move into the presentation. So Rob's a scientist with a BS in chemistry and an MS in health physics from University of Cincinnati. Rob joined the EPA in 2003. Prior to that, he spent 12 years with the Department of Energy, overseeing large-scale remediation while developing real-time radiological survey instrumentation and procedures. So Rob's research at EPA has focused on understanding and dealing with contaminant threats to drinking water distribution systems, including helping to develop TIFA spot and tools for real-time modeling, the EPANET, the series of models. And Rob helped coordinate the establishment of the open source project that led to the community open source software project for EPANET. And our next slide is Feng Shang. Feng is an environmental engineer with a BS and MS from Tsinghua University in China and a PhD from the University of Cincinnati. As a postdoc, he worked at the EPA and wrote the initial code for the multi-species extension to EPANET. In 2018, he joined an engineering software company called Innovise, where he worked on similar projects. And then in 2019, he rejoined EPA, where he focuses on researching hydraulic and water quality issues in water infrastructure systems. And with that, I'm pleased to introduce or give the podium to Rob, who will carry us on from this point forward. Thanks.
Thanks, Tom. And first thing I'll do is share my webcam here for folks. Hopefully you can see me. And well, thanks everyone for attending today. Today, Feng, Shang, and I will provide an introduction and some example applications for the water distribution system modeling software called EPANET. And here's an outline for our webinar talk today. First, I will provide a brief introduction to EPANET, and Feng will introduce some example applications that you can investigate using EPANET and your network model, or just to experiment with. I'll first highlight our new release of EPANET, which is version 2.2.0. And this latest release was made possible by our collaboration with the open source community at OW, Open Water Analytics, which I'll talk more about later. So what is EPANET? Well, the name EPANET is not an acronym, and we prefer the all caps designation. EPANET is a Microsoft Windows-based computer program. It is a desktop or laptop application, standalone application. EPA provides 3 versions of EPANET: a graphic user interface version, DOS, folks remember DOS, disk operating system from Microsoft, command line version, and also a programmable toolkit version for those that want to develop or build their own custom software applications. EPANET is used for modeling and analyzing a water distribution system. EPANET takes as input a water distribution system model, that is a pipe layout, outputs a hydraulic and water quality parameters on the state of the water distribution system. EPANET is an open source software product that is free to use, free to download, free to use. Today's talk is focused on the graphical user interface version shown here in the graphic to your right on the slide. Let's first consider what a typical water system is composed of. Here's a schematic of a typical water system, which includes facilities to transport the water from its source to treatment to customer distribution. EPANET models are often constructed to represent the distribution system, for example, from treatment to distribution to the customer meter. Here are some terms and definitions I'm going to go over that will help with using EPANET and understanding it. And to get started, and acquainted with, these terms are kind of important. So first, we have a water distribution system itself. And what's that refer to? Well, it refers to a collection of pipes, tanks, pumps, valve control systems, and other components that work together to move water from a water source or treatment plant to the individual users or their customer meters. The network model, which I'll talk about a lot in this presentation, and Feng will talk about, is for EPANET as a text file. It has an extension of .inp that labels it as an EPANET extension or an EPANET text file. The water distribution system is a representation. It's a pipe layout infrastructure map that lays out where the tanks, pumps, valve control systems, and other components are. The hydraulic model is a network model that's been simulated in EPANET for hydraulics. The water quality model, similarly, is a network model simulating EPANET for water quality. So here's some more terms and definitions. There are two types of simulations that can be performed with EPANET. That is a steady state simulation and an extended period simulation. Feng will talk more about these later, but first recognize that water distribution system modeling using EPANET is a process for gaining an understanding. That is a process for understanding how a water distribution system is operating, or perhaps could be operating, or could be designed, or enlarged, or changed in some way. Water distribution system modeling is a mathematical process connecting a physical pipe infrastructure model with the mathematical equations of hydraulics and the chemical properties of water quality through modeling and simulation in EPANET. It's an empirical process. So why develop a model? It's clearly a model essential to using EPANET. Well, why go to the effort? Well, central to using EPANET or performing water distribution system modeling is the need for a model, also known as an infrastructure model or network model. The motivation for developing a model may be for performing planning exercises, capital improvements, maybe to better understand water usage and conservation needs, or how best to implement a pipe or tank replacement project. The motivation may be for performing some needed design, or maybe to better understand operations, how best to solve a particular operational problem. A model could be used to do that. Water systems are complex operations involving often many thousands or tens of thousands of interconnected components that must work together to efficiently and reliably deliver high quality potable water to its customers. Understanding these myriad of processes and operations involved in the complex operations of water distribution system conveyance requires data and information, and most notably a network model. And here's a picture of a network model to the right, and of how it'll appear in EPANET. So EPANET supports hydraulic modeling and water quality modeling. And just to reiterate, EPANET is a software program that allows a user to easily perform hydraulic and water quality modeling. Hydraulic modeling requires the hydraulic states of the system, or it determines hydraulic states of the system. For example, the flows, pressures, and tank levels of the system. Water quality modeling determines the chemical state or water quality of the system. For example, water age, disinfectant levels, and contaminant levels. So here, stepping back a little bit to give a brief history on EPANET and give some recognition to its creator, shown here. It was first developed by Lou Rossman. And the first non-beta release of EPANET was in 2000. It was version 2.00.00. EPA's latest version of latest release, that is, of version 2.00, was released in 2008, and that was 2.00.12. And while working for EPA before he retired, this was Lou's last official release. Maintenance and advancement of EPANET is now being performed through the community collaboration at Open Water Analytics. While Lou retired in 2014, he continues to support EPANET at Open Water Analytics. And the release I'm going to talk about today, many thanks to Lou and the others from OWA that helped to make this possible. The community collaboration at Open Water Analytics was begun in 2015 with the announcement by the International Water Distribution Systems Analysis Community, a subset of the American Society for Civil Engineers, in their desire for establishing an open EPANET. Along with the announcement, a steering committee, a development committee, and discussion forum was established. Open EPANET is called OWA-EPANET at their official repository. And I'll get to that in a little bit. The open source software repository for EPANET hydraulic and water quality engines are at GitHub/openwateranalytics, all one word, /EPANET. And I'll just switch to that real quickly so that you can see that. This is the opening page of Open Water Analytics EPANET. So I'll refer to that as we go through the presentation. If you want to download EPANET, and there's a couple ways you can do it. You can go to EPA's website, which is shown here in the slide, and download the self-extracting installation program for EPANET, as well as a user's manual or the toolkit and extensions. You can also go to our US EPA GitHub site, which is located at the address shown here on the slide, https://github.com/USEPA/EPANET 2.2. And I have a couple pictures here to the right of the slide that show both our website, where you can download EPANET, as well as a screenshot of the release page at our GitHub site. And I'll switch to that momentarily so that you can see it. Similar to the GitHub site that John Burkhardt showed earlier, the GitHub site for EPANET also has a release section or a release page, if you will, on the right side of the screen that you can go to get the latest release. And you can find that here with the various artifacts I'm going to talk about in a little bit, along with that release. So that's how you obtain EPANET and then download the necessary files. The other thing I wanted to mention here is that I'll go on to the next slide, I guess. Installing and running EPANET. For the self-extracting installation program for EPANET, it's provided in the file name EPANET 2.2_setup.exe. Installing this application on your Windows computer will often require administrative privileges. The installation program installs EPANET 2.2.0 and installs an integrated help file, so you can get help as you run the program, a standalone tutorial, an HTML-based tutorial, and some release notes showing what's all in EPANET and what came before it on this version. This is all within the Microsoft Windows Start menu. EPANET 2.2.0 will or should work with Microsoft Windows versions 7.0 or later. I'm currently running it on a version 10 right now. Depending on your Windows file management, the example networks may be a bit hard to find because they are placed in a subfolder named EPANET projects/examples in your documents folder. So depending on where your computer how your computer is configured with respect to your documents folder. It'll place them there. So running EPANET uninstalled can also be done. And for those individuals that are maybe not able to install EPANET because of insufficient administrative privileges, perhaps the computer's been locked down or something, you can download the file EPANET release file named EPANET 2.2.zip. And this zip file contains everything you need for running EPANET, including the integrated help and tutorial HTML programs. All you need to do is download the zip file, extract the contents, and then double-click the file named EPANET2w.exe. And this will open the EPANET application, the graphical user interface version of the application. The file name in the same folder, run EPANET.exe, is the Microsoft DOS version that I referred to earlier. And this is a command line version. Again, this option, using the zip file and then just extracting the contents of that zip file, does not require administrative privileges for many users to run an EPANET, as well as the integrated help and tutorial. So actually, before I go on to a brief hydraulics review, let's go to back to these web pages and just take a moment to look at the EPANET web page where you can download the software. And if you go to epa.gov water-research/EPANET, you'll come to a home page that looks like this. There's a little introduction to EPANET, and then the download software is broken into the 3 components depending on this, whether you want just the software, the toolkit and extensions, or the source code. And these are now configured on the software side at the top to go to the GitHub page. So you can download the program here, or you can go to the GitHub page I referred to earlier. In either place, you'll be able to download the software. So with that, I'm going to go back to the presentations and talk a little bit about a brief hydraulics review. Given the time frame we had here for the webinar, we really need to condense this down to a slide. So I apologize though to those folks that need more of an introduction. But there's 4 basic assumptions with respect to EPANET that are really critical about understanding hydraulic flow in these types of pipes, water distribution system pipes that the EPANET models. First of all, the flow it's incompressible flow, and 2, it's turbulent flow. So the fluid is well mixed, and it's a closed pipe flow. And furthermore, contaminant injections are modeled as a mass per unit time. So there's no added volume that can be added to the pipe. It's just a mass per unit time. And of course, the assumption there is any volume would be added would be small in comparison to what's already being modeled or contained in the pipe. So it's a very small uncertainty. And the 4th assumption is that the pipes are full. And if you would like more background information on this, I recommend 2 books. One, the Advanced Water Distribution System Modeling and Management book by Hasted Methods. And the other, a Water Distribution System Handbook that L.W. Mays was the editor on by McGraw-Hill handbooks. Both of these are very good references. Next, I want to talk a little bit about units, EPANET units. EPANET uses both English units and metric units. And on the English side, the units are, of course, gallons per minute. And a notable reference here to point out that may be helpful to folks is 1 million gallons per day corresponds to 646 gallons per minute. And a flow of 1 cubic meter per second corresponds to 1,000 liters per second. And finally, the choice of units within EPANET, whether it's US or metric, are specified by the choice of flow units in EPANET. So you choose the flow units, and then that specifies all the other units. And now another slide, or final slide, with respect to units, and then also some definitions. Pressures can be either, again, US or metric, and if it's US, pounds per square inch. If it's metric, it's pascals, depending on the choice of these pressure, depending on choice of flow units. Choose flow units, and it determines units for pressures. A good reference number to remember is that 1 foot of water corresponds to a pressure of 2.31 pounds per square inch. Also, generally speaking, the minimum pressure in a water distribution system is 20 psi, while the maximum pressure should probably range from 80 to 100 psi. Again, these are in English or US units. In EPA nomenclature, nodes include junctions, tanks, and reservoirs. Links include pipes, pumps, and control valves. Links must have both a start and an end node. This is something that differentiates EPANET from several or perhaps most commercial software programs, in that these links have to have a start and an end node. In EPANET, reservoirs are nodes with an infinite external source or sink of water to the network. So getting started, let's talk about how you can get started with EPANET. And I guess a note here on this presentation. This is very much an introduction, and for those folks that are already familiar with it or have done a lot of distribution system modeling, I apologize for the introduction. But for those that have not used EPANET and are interested in how to just get started, there's 3 basic ways you can do it. One is the HTML-based tutorial, and this is an integrated help tutorial. You can access it, the help, from the start menu or in the extracted, if you use the zip file, HTML file. From the menu bar, in EPANET, you would just choose help and then help topics. I'll take a moment here and switch to that. So now you should see a screen of EPANET. In this network that's here is example 1 that comes with EPANET. You would just go to help and then help topics, and then the help menu comes up, which is very helpful. If you want to find anything, you can go to the index or the search, or you can just browse it in that manner. Another way you can get started with EPANET is by just opening up the user's manual and then experimenting with one of the example networks or your own network if you have one. And with both the tutorial, the user's manual, and the software, it makes it quite easy to get started and get a little understanding of EPANET. So when you do open up EPANET, you're faced with some different screens that open. And the graphical user interface, which again, the version I'm talking about here, has 4 main components. One is the menu bar. Another is the network map. The third one is a project browser and the property editor. Looking at your at this graphic to the right on your screen, these are all labeled. And the network map is where your network will appear. This is where you'll run simulations in and you'll see the results, which are kind of shown here in color. The browser, the project browser, is what you will use to run and stop simulations if you go to map, or through the data browser, you can access particular elements within your network, whether it be tanks, nodes, tanks, you name it. And then up across the top is the menu bar. And then of course, right below that is what's called the toolbar. And you use the toolbar for constructing a network from scratch if you want to do that. So you can, for this workspace, you can also refer to Chapter 4 of the User's Manual for a detailed discussion of EPANET's workspace. In the following slides, I will provide a quick walkthrough of some of these screens. But don't forget, if you get stuck or have any questions, open the integrated help within the menu bar. Again, help topics, and you can browse for any of these screens and figure out what they are. So the menu bar, I selected a few of these items that are probably some of the more important ones, and ones that can be maybe a little confusing to folks just starting out. Moving from left to right on the menu bar of EPANET, under the file there's one called Preferences. And Preferences allows the user to set some general and format preferences. Although not shown here, the Formats Preferences screen allows the user, that would be the other tab right there if I had a screenshot of that, it would allow the user to set the number of decimal places for node and link parameters. This is important. This often trips people up because they want to see more significant figures in their map or their animation after they've run a simulation. So you want to do that in the Format Preferences section. The options box, the next screen, moving again from left to right, allows the users to set the map view options for the network model. You can enlarge or shrink the size of nodes and display, symbols. There's lots of features within this options view to tailor your map view. Moving on over the project summary bar at the top. If you click on that, say somebody gives you a pretty complicated model, you open it in EPANET, and it's like you're just faced with this dizzying array of nodes and pipes. You can go up to the project summary, and it will provide a summary, as you can see once you open it, of what's all in the model: the number of junctions, the number of pipes and whatnot in the system, in your network model. So below that is a screenshot of the calibration of screen that you can use to open. It's calibration data, and this allows you to upload data. It's a text file data, contain the calibration data for network model. It's in the text file, it would just contain the location ID, the node, for instance, time of the measurement, and the value that it is, and that'll use that to compare against the actual model runs after you've made a simulation. And then moving on over to the right, the final screen is a defaults screen that's under the project tab of EPANET. This allows the user to edit the project's default properties. Defaults make it, setting these up ahead of time makes it easier and faster to build models from scratch. Maybe you have a bunch of models you want to build, and this would simplify that process. Now I'm going to switch over a little bit to EPANET again, so that I'm going to so I can show this. I'm going to close the help a minute and show the this top screen. It's one thing to see it in the slide, but then actually to see it in the program, it's can be a little different. Under the file menu, you click that, and you can see the preferences tab that I went over. And there's also a number of other options. If you want a new map, if you want to open another existing network, or if you want to save or import export models as well, you can in maps, and you can use these features. And then the view that I spoke about on options, that's all the way down at the bottom. And then of course on the project, the summary I mentioned is right at the top. And you open that, you can see the summary for this example, network 1. And of course, there's several others. There's a report feature that I'm not talking about here, but they're fairly self-explanatory. And of course, the help that I mentioned. So moving back to the presentation, I'm going to talk about next the property editor. So again, the 4 components of the EPANET workspace was the map, the browser, the map data browser, the menu bar, and the property editor. So the property editor is the screen that allows you to edit the properties of a particular network. And in this particular screen, you can see that this is a junction that's come up. So the first line, it's a junction ID. It gives a coordinate, X and Y coordinate. The description blank is left blank, but you can go down to the more pertinent information, the ones that are asterisks. Those are the ones that are required. You can see the elevation, the base demand that was assigned with this particular node, and if it had demand pattern, and so forth. The bottom part of the property editor for a junction will be what comes up after the simulation is run. This will show you the results for this node after it is run. The network map itself is shown in this slide. So a user can build a water network model from scratch using a toolbar I mentioned earlier and showed within EPANET. They can run a simulation and they can view the simulation results. Results can be viewed either as a time sequence animation or in graphic or tabular form. So this top screen shot that I put in here to build a network model, you would just go to toolbar and you would drag and drop items, whether it's a node, a tank, or pipe, and basically connect the elements. The bottom figure shows a simulation that's been run with then a selection made with respect to both water quality and flow, hydraulics. And these are user selected, and then I pasted in here a graph that can also be created after you've run a simulation. So now I'm going to move on to the project browser. And I've already mentioned this, but I'll reiterate that the project browser has 2 tabs. One is the browser data tab to the left of the screen, and the other tab is the browser map screen to the right. And of course, in the middle is a property editor that I just spoke about. The browser data tab allows a user to access a network model objects by category and open them into the property editor, as you see here. At the bottom, in the middle, at the bottom of the browser data tab are buttons to add, delete, and edit objects. The browser map tab allows a user to navigate an animation. That is, select parameters from the drop-down boxes for nodes and links in the time in a simulation to be viewed in the network map, and then start and stop a simulation. So that's the basics of EPANET. And before I talk about this slide in terms of recent improvements in 2.2, I'm going to go back to EPANET and just show, again, we have here example network 1, which comes with EPANET. And there's a couple ways you can run this. You can go up to this lightning bolt that when you hover over it, it says run. Or you can also go up to the menu bar, and you can run it from up here. And up here, you'd run it from run analysis. And when you do that, it's a small model. It runs very quickly. Now, what you don't see on this screen is the is the project tab that I was just talking about. And that's because I've moved this to my second monitor. And sometimes these screens can get a little bit displaced. And so you can reposition these, enlarge or shrink these depending on your screen or the monitor you have on them so that you can show it all. So if you go over here to, as I indicated, the map browser, you can show, let's just say demand on the nodes and then flow on the links. And you see they automatically light up. If you want to change the what's in your legends here, you can right click on it and change them appropriately. And notice that the significant figures are just 2 decimal places rather. And if you want more, you need to go to the preferences to change that. But you can change the color schemes and whatnot through those by right clicking on those legends. So that's how you open EPANET and then open a network model and then run it. So now I'm going to switch back to the presentation and just talk really briefly at high level on the significant improvements that were done to EPANET 2.2. So some of the most significant improvements are outlined here, but there are many others. And the first that I'd like to talk about is this pressure-dependent demands and hydraulic analysis that was added. This was significant. You know, it allows you to analyze a system when you, more realistically, when you get negative pressures. You may want to analyze that in a pressure-dependent situation to see how it looks, because the results can be quite different. There's also an option that was added to allow full tanks to overflow, like they would do in real life, or could do in real life with of course, that's consequences, and it would be good to be able to model that. There were options added to ensure a more accurate hydraulic analysis. There were features added to show or handle a more robust handling of low and zero flow hydraulic conditions. And of course, another one that was done is this improved mass balance results for the water quality analysis, which was a very important one as well. So there was also, I guess, finally an enhanced API. This is application programming interface function for those that want to custom build their own applications. And this enhanced API function library for customizing EPANET can be found at the wateranalytics.org /EPANET for those that want to develop their own applications. So where do you go for help? Well, if you have general information, of course, you can go to our US EPA website and use the link at the bottom. That's a contact us link if you have questions. Emails will then come to us. You can go to our US EPA GitHub site for general information, user interface information, like the graphical user interface version I showed here today, or you can use the contact email of EPA-ORD@epa.gov. If you have questions related to hydraulic and water quality engines, specifically and the changes were made to them, I recommend going to this site, the https //github.com openwateranalytics/EPANET/wiki. And you can often find your questions through this wiki or the community forum at the community.wateranalytics.org /link. And finally, if you want to contribute to EPANET, please go to the Open Water Analytics /EPANET/issues and get familiar with GitHub and what the current state of EPANET is. Right now, they're working on version 2.3 and become a contributor. So with that, we're going to go to the questions. And I think this is where our friends at Cabness will introduce some poll questions. Good. Everybody got it. Modeling pressurized closed pipe system. That's the first question. So, if anybody has any other questions, of course, after these poll questions, type them in, and Tom will help MC those out to us. And again, we're going to save most of them until after Feng's talk. So.
And Robert, we're launching question 12 right now. Where can you obtain EPA-NET?
I see that, yeah.
Okay.
So, okay, what other questions do we have, Galen, on form? Oh yeah, who developed? So the correct answer to this question is, I'll wait until we get about 40-some, 50% of the vote. Yeah, the answer to this question was OWA/US EPA. OWA took the lead on the engines, the hydraulic and water quality engines updates. And US EPA took the lead on the user interface and the user's manual. So was that the last of our questions then, Galen?
We have one more on EPA-NET.
Okay. Apologize, I don't remember what all we wrote. Okay, so, oh yeah. If you want to help, volunteer to help maintain and extend EPA-NET. Right. You go to the github.com/openwateranalytics/EPA-NET. Great. That's the correct answer. So with that, I'm going to move back to you, Tom.
Great, thanks, Rob. Great presentation. I've got a couple questions for you. There's a number of questions, but many of them are a little detailed, and I think Feng's going to speak to many of them. So, okay. But I'll ask some. There are still some that I think pertain to you. So for EPA-NET, one question is, can you use it for very large, complex utilities, such as utilities that have 500,000 or 1 million meter boxes?
Yeah, so when we talk about meter boxes, I assume they're talking about service connections. So the question is, of course, is the model represent that many nodes, right? Is there a one-to-one correlation between meter boxes and nodes or junctions in the model? And but the long and the short is yes, EPA-NET can handle very large models. I've certainly worked with EPA-NET in the tens of thousands of network nodes and pipes each. 60, 70,000 plus. I know of others that have done over 200,000, maybe as much as 250,000. What's going to be a factor in that is your computer. EPANET handles it pretty well. The issue is, how much system resources you have on your computer. What other things are running?
Okay, great. Yeah, excellent. Okay, here's one. So is 2.012 and 2.2 cross-compatible? So if you create a program in one, can you then run it in the other?
Yes. There's generally speaking, that is the case.
Okay. Can EPANET analyze for water hammer conditions?
So those transient conditions, and no, EPANET is really not set up to do that. That's not been a feature that's been added in.
Okay. What about what type of map models can be uploaded into EPANET?
Okay, so the map models are EPANET has a map feature in it, but it's specific to the program. It's not a GIS-based map. So you're really limited to uploading backdrops to maps for visualization purposes. So you're really quite limited there. Now we do have efforts underway to develop some type of GIS interface capability with EPANET, and we have a development site out there that has a prototype version of a Python-based UI for this, but it's still under development. It still has the same look and feel of EPANET, but it has the capability to work with both shape files and JSON files. So you could interface between EPANET and say ArcGIS or QGIS, something like that. Otherwise, you have to go to the web and Google. There are parties out there that have features for converting an EPANET model into shape files and vice versa. You just have to you'd have to Google for them. But you're really limited with EPANET to answer the question.
Okay, we already asked how large a system could be modeled. How small of a system can be modeled with EPANET?
Well, just 2 nodes, as small as you want, really. As small as it would still represent a complete system, right? Input and an output for water.
Can you model premise plumbing systems?
That's a very good question. So there's a group of us here, John being part of it. We're part of a premise plumbing modeling committee that is working on modeling premise plumbing situations with EPANET, and the answer is yes, you can. You just need to develop a premise plumbing model, network model for your system.
Okay.
For your building, whatever it may be.
Maybe a couple more, and then we'll go to Feng's talk because he might cover some of these. Okay, so here's a basic question. When you say PSI and pressure, do you mean absolute pressure?
Absolute pressure. Yeah. So this is so the pressures are being modeled are the pressures both elevation pressures and then flow pressures. Yeah, they combine. I believe they're absolute pressures. Yeah.
Okay. And I think some of these, in terms of, they're getting into more of applications for DBPs and disinfectant residuals. So we'll hang on until after Feng's talk, and then both of you can answer these perhaps after that. Here's one last one for you, Rob. So if you were just getting started, what is the simplest way? Self-extracting. The two different versions of EPANET 2.2, the self-extracting and the zip non-installing file. Which way is the easiest way to get started?
I think the easiest is a self-extracting in a way. The only thing can be a little confusing with that is within the Windows file architecture structure, you know, knowing where you download the zip and then zip file and then opening it and managing those files so you can find them. But that's probably the easiest if you're working on a computer that has any type of administrative restrictions, you know, to installing programs. Some people don't have admin privileges but are able to install EPANET. So it's going to be specific to your particular situation. But I think the uninstalled version will work just as well, and it's probably the easiest.
And is there a tutorial for drawing a map in EPANET?
There's a tutorial, yes, that'll walk you through drawing an example map. It's an HTML tutorial, and you know, sometime back I've gone through it. I think it's very helpful.
Okay, great. I'll save some of these other application questions for a little later. So hang on, Rob, and
okay.
And let's throw this over to Feng, and Feng can give the application examples portion of the EPANET program. So
okay.
I'll hand the podium to you, Feng.
Thank you, Tom. Can you hear me?
Yes.
All right.
Yes, we can.
Let me present my screen. Cleared. Can you see my screen or not?
Yes, I think we can now.
Okay, good. Oh, okay. All right. So I'm going to talk about some EPANET application today. And let me move this. Okay. So EPANET model can be very simple. Some audience ask about how complicated model can be. It can be quite complicated. As Rob mentioned, it can have like 250,000 pipes, and thousands of valves, but it can be very, very simple. So since I noticed the majority of the audience didn't use that before, so I think I can show you how to build a very simple network. So here is the EPANET like main window. When you open the EPANET, you can see this window. So first I can create a junction, basically is the user junction, and then I can create a reservoir. Then I just use a pipe to connect this reservoir and the user node. So you can see it can be very, very simple. So of course you need to specify user demand at the junction. You can specify reservoir head, how high it is. So this is the simplest model I can think of. You can model a city as a junction with like 1 million gallon per day water, and you have a high elevated water sources. So basically that's the very simple example I can think about. So you can run the simulation, you know, you can here, I bring the browser here, then you select this reservoir. You can see you can have a head. Basically, I put a 50 feet here. Then I can put a junction with 0 feet elevation, base demand. This is gallon per minute. I put a 700. Basically, it's 1 million gallon per day, roughly. So I just run it. You can see run was successful. Then I look at the node. Yeah, I have total head. This is a total head 47.87 feet. In terms of absolute pressure, it's 20 psi. So that's, you see, okay, then people say, oh, we meet the minimum pressure of 20 psi. This city as a whole has enough pressure. But of course, you can make this one junction very complicated, become a city with 100,000 pipes. So that probably answers some of asked questions, how simple it can be and how complicated it can be. Then I go back to my presentation. First, I will talk about EPANET hydraulic applications, then I will talk about water quality. EPANET can model hydraulic conditions over one or more than one period. I should emphasize there is no transient or water hem analysis in EPANET. There's commercial software with the name Hammer, Surge. This are to model transient analysis. EPANET cannot do transient analysis. So it's also called extended period simulation. So basically, it is a series of steady state simulation. In this model, demands need to be assigned. Power demand is the most dynamic input of the EPANET model. If you want to have a really good model, of course, you need to have really good input. Water demands need to be assigned to every user junctions. Of course, we have pipes, pumps, valves to transfer water from source to consumer ends. There are two kinds of hydraulic analysis. Steady state. What I just show is basically steady state. We have a snapshot analysis with fixed demand, like just 700 gallon per minute demand. So it's a snapshot. We can see, okay, at this kind of demand, how the system can perform. Usually, people assign peak demand into the junctions, so have a snapshot to see if the hydraulic condition can be, like minimum pressure requirement can be met. Also, we can do extended period simulation. In this kind of simulation, user need to assign the changing demand to user nodes. And typically we user IC do a couple of days, 2-3 days, even a week of extended period simulation with 1 or 2 hours as a time step in order to model the seasonal peak days, like the very hot day in August, how the hydraulic condition is when people use lots of water. Okay, before I go into the hydraulic presentation, we will pose 2 questions. Okay, that's kind of expected because many of the audience, they never use EPANET, so probably they never use the pattern, the EPS. So 2 to 10 is normally what we saw in terms of water demand patterns. I will explain water demand patterns in the application. Okay, then the next question is about pressure. Yeah, okay, 50%. It's kind of, yeah, I never work in the field, but I already heard that it's 20 psi as a minimum pressure. But some utility, I know they talk about higher than 20 psi as their minimum pressure. So okay, that's very good. Okay, now I'm talking about extended period simulation. The pattern time step can be set to be very small, like 1 minute. As people ask about a premise plumbing application, I think one very important factor is the time step. The time scale is much smaller than for a large city planning model. So I know John Burkhardt, he used some in his premise plumbing model uses seconds as the time step. So yeah, so usually it's 1 hour or 2 hours, and each node need to have its base demand, which usually is the average demand over the day. But we know the demand change dramatically. It's even for the same junction, it may be very low in like 2 a.m., 3 a.m. It's pretty high in like 9 p.m., 10 p.m. So we do this, EPANET does this by combining base demand and demand pattern. Because we can have like 10,000 nodes in a system. It's quite laboring to specify 10,000 demand patterns. Some of them are very similar, so multiple nodes can share the same demand variation pattern. So here you can see, here is the pattern. So the pattern time step is 2 hours, so it fluctuated over 24 hours period with 2 hours time step. If you assign this same pattern to 2 nodes, you will see different user nodes at the 2 different junctions. You can see the base demand is different because the pattern is 1 here, value at the beginning, so 150 and 100 are the base demand or average demand of these 2 nodes. So this way you can have dynamic user demand at every junctions with only 1 pattern and 2 average demand. And the simulation results, you can see if I show pressure, you can see they've kind of follow the same pattern in terms of pressure change because they share the same demand pattern. The demand change pattern is the same for these 2 nodes. And this is a tank, this node 2. I will demonstrate the model. This is a net1 model, the example 1 in EPANET example folder. So you can see here the tank level going up, then drop down. Why? Because we have a pump in the system. When the pump is on, the tank is filling, so the tank head, the tank water level keep rising. When the pump stops, usually in some peak electricity price time, then the tank will drain and will provide the water to the system. So here I can show file opens is net1.net is as Rob showed before, is an example file coming shipped together with EPANET. So here I just run the analysis, then I can see you click this tank, you report, graph. We are interested to see the tank head, the tank head. You can see it's what I showed before. The tank is filling during the first about 12 hours, then start draining to provide water to the system, then going up when the pump kicks on again. See the pump, you can also use report, graph, flow. You can see that's how pump works. Pump provides water to fill the tank and the user demand. And when the demand is a little bit lower, the pump shut off, the tank provides the water. So you can see this shows how the extended period simulation worked. All right, then back to my presentation. Now I'm talking about pressure. If you have ever run EPANET, maybe you have seen negative pressure warnings, but as I said before, there are no transient analysis in EPANET, so we shouldn't see negative pressure. But why negative pressure warning in EPANET modeling? Basically, the system basically the negative pressure warning tells you the demand cannot be met. So you assign too much demand to the system for it to deliver, basically. So what we should do, if you are planning engineer, you say, oh, maybe we need a higher, we need to increase the elevation of the tank, or we need to provide a more powerful pump to provide more head to the system. That's probably what we should do if we really use EPANET to simulate the system and see lots of negative pressure. As Rob mentioned before, EPANET 2.2 has a pressure-dependent analysis. This is a very interesting analysis. Basically, it can automatically adjust the demand in order for the system to deliver. So basically, if you assign 50 gallon per minute demand at this node, and the system cannot deliver, it will reduce the demand from 50 to whatever it's possible. So when user assign demand, when the pressure is high enough, of course, you will still get user assigned demand. But if the pressure is very, very low, you will have zero flow at that node. This is more kind of mimic the reality. Think about a fire flow analysis, right? If you want a very, very high flow, but the pressure is not enough, you won't get so much flow from the hydrant. So pressure-dependent analysis is kind of be able to do this kind of analysis. Again, I will open another one. Again, it's an EPANET example model, net 4. So I put some text here to show the node ID. So this one, node 9, is problematic because why? It has a base demand of 75. And here, other node all has 25. So this has very high demand. And when we run it, where is my browser? View. Here I did because here is pressure dependent demand. So you can see here if you see the report, one node has its demand reduced by a total of 7.83. That means the 75 cannot be met. So you can also use the table, show the nodes. You can see here. Every other node, 25, or sorry, here the unit is liter per second, is international unit. Here we don't have 75 liter per second anymore. We only have 61.63 because if we want to have 75, we will have negative pressure warnings. So basically the 75 liter per second demand cannot be delivered. So the hydraulic engine adjusts the demand to meet the hydraulic condition of the system. So this is a functionality in EPANET 2.2 is quite useful, especially for some like fire flow analysis, if people are interested. Here I put the comparison of the traditional EPANET analysis and the 2.2 pressure dependent analysis. You can see that every node is the same in terms of demand. But here, the traditional simulation have negative pressure, negative 2.3, 2.73 here in the node 9. But with the pressure dependent analysis, we have adjusted demand with all positive pressure. So this shows how pressure dependent analysis can be used in system analysis. There are some other hydraulic functionalities, like we can set controls. So basically we can control how pump works based on, for example, tank levels. So here is an example. The pump 9 is open when the tank elevation is water below 110. When it's above 140, just turn off the pump. Of course, you can define pump curve, 1-point, 3-point pump curves. You can also have all this control valve, pressure reducing valve, pressure sustaining valve, and flow control valves. So all these valves can be modeled. And another handy capability is the pump efficiency and energy analysis. Based on the flow condition and the pump curve, you can analyze the pump efficiency. And also, if you input energy price, you can know how much pump operation will cost in terms of electricity bill. Okay, I'm done with the hydraulic analysis with some very simple examples. Now I'm going to talk about water quality analysis. Basically, water quality analysis, we can have 3 types of water quality analysis: water age analysis, trace analysis, and some chemical analysis, basically chlorine decay, as some people may have asked. One thing we should emphasize is this EPANET water quality analysis is a single species analysis. So if you want to model complicated reaction between natural organic matter and the disinfectant and the generation of DBP, traditional EPANET cannot do this. You can model like first order decay of disinfectant or first order growth of DBP. But that's probably a limit of the EPANET water quality engine. But it still can be very useful, especially in terms of water age analysis and trace analysis and first order decay chlorine modeling. Then there are 2 poll questions about water quality. All right. Yeah, okay. Oops. That's, yeah, quite interesting. Before, when the first years ago, I never thought the water distribution system can have a very, very old water, like more than 1 week old, because it seems a little bit scary. But in some analysis and some tracer analysis, after some field and model analysis, I realized it can happen really in the water distribution system. So I here see, yeah, there's almost half of the answer saying it's 7 days or more. Probably that's really what happened especially in fairly large system. Okay, next poll about the disinfectant. I brought this question to the poll because I don't know myself, so I'm really curious about things the audience combined many years of experience, engineering experience. I'm just curious about that. personally, I'm not sure at least. So looks like many people think it's in the tanks, on the pipe walls. Yeah, likely. I don't know. So if really the lots significant disinfectant loss happens in the tanks, then probably that also means tank is the place lots of DBP were generated, right? If we think about the reaction, the reaction of disinfectants with organic matters, yeah, then we can do probably lots of work can be done on the tank to improve DBP management. Anyway, it's good to know the answer. Where is it? Okay. Then first I will do some animation. I think Rob didn't show animation, right? So I'll open this called net2. The net2 again is another example network coming with EPANET. EPANET example folder contains 4 quite simple network. This is called net2. First, I will put okay. I will select water quality option. Quality option. Originally, it's called fluoride because it's some interesting study. Here, I will do water age analysis. Water age analysis probably is the simplest water quality simulation you can do in EPA, because all you need to do is just in this quality option browser, choose water age. You don't need to specify anything, any parameter or source or whatever. You don't need to specify. Then I will put age as node view. Then run analysis. Successful. Here you can see there is some animation bar. You click, then you can see here 1 hour, 2 hour, 3 hour, 4 hour. You can see the water quality start to change. And at a certain point, we will notice this yellow or red means 12 hours older or 24 hours older junction show up. Just look at this part, right? This part have pretty high water age. And who is to blame? The tank, right? Here you see the tank is always red. So, and really, okay, let me stop this animation. Okay, let's see the tank water age. Report, graph, water age, right? Here, yeah, the nodes is 26, basically the tank ID. You can see, it's interesting, right? It's kind of increase linearly. That's pretty bad, I think. So when the simulation time is 50 hours, the water age is 40, 42, 40, close to 50. It's kind of linear growth. I think the reason is because the tank is very large, and the turnover of the tank is pretty low. So lots of water just stay in the tank and getting older and older. Even some, you know, when some fresh water comes in, the dilution is really negligible. And if we really look at the node junction, very close to the tank called junction 25, we see the age graph, age. You can you can see here the age keep going up. This part is basically the high water age is when the tank drain. When the tank drain, this junction 25 receive tank water with very high water age. When the tank is filling, because the junction receive kind of fresh water from that pump station, the water age is low. So we can see, okay, large tank can really contribute to quite high water age in the system. One thing we can do is probably we can plot them together, graph. I already have 25. Then you can click this tank, add, and show this water age. You can see, right, they overlap when the tank is draining. When the tank is filling, the node 25, the red curve have quite a low water age. So Water age analysis is very simple to do. You don't need to specify any water quality parameter. You don't need to specify source, but you can still get some very interesting insight into a system, I guess. Okay, this is what I just showed before. Node 26 is a tank. Node 25 is the user node just outside of the tank. It receives very old water from the tank when the tank is draining. It has a very fresh water when the tank is filling and the water comes from the pump station. Okay, the second water quality application is basically trace analysis. Trace analysis is also kind of easy to do. You just need to specify where to specify the trace source, because people are interested in where the water comes from. Usually, some utilities, like especially in California, they have groundwater, they have surface water, they have multiple water sources. So we want to know where the water comes from. Then trace analysis is kind of handy to do this analysis, and the calculation is also very fast because it's basically there are no chemical reaction or whatever. So then let me go back to the EPANET application. This time I'm using Net 3, which also shipped with the EPANET application. We have two sources, river and lake. And one thing is to notice is that in EPANET you have to do trace one by one. You cannot say I will do multiple trace analysis. So first I want to trace the lake. So in option, in quality, I choose trace. Here you can see already lake is here. So you can do analysis. Then I pick up some node here. Okay, here from the map, more if the hydraulics is not that complicated, it seems it will receive more water from river, right? So let's see, less water from the lake. So I will plot graph trace lake. So you can see at the beginning 0 because the initial condition it receives water from nowhere. Then we can see during this part we have like 9% lake water. So in order to double check, we can do the river trace. In the quality, again, parameter is trace. Trace nodes we put in river. Okay, river. So basically this node is called river. Then I do it again, run analysis. Then I will see. I remember this node. Yes. Okay. I'll report graph, and I will see the trace river now. You can see during this part, like 90% of water from the river. Ideally, this two different sources, if you do two simulation, you add them together, you should have 100%. But sometimes it's less than 100%. Why? Because you have tank water and you also have some initial condition. But if you run the simulation really, really long, like 7 days, 9 days, probably you will more likely you will see 100% if you add the two simulation results together, because the initial condition will be eliminated. The memory will be gone after a very long time simulation. Okay. All right. I just show you two very simple but very useful water quality analysis. One is age analysis. One is trace analysis. Then let's go to okay. Yeah, this is just what I show to emphasize the sum of these two simulations should be close to 100%. It shouldn't be higher than 100%. Then we'll have the model has trouble, because right, we cannot have like more than 100%. It can be less because of initial condition. Then let's see some chemistry. I'm sure lots of people in the audience are chemists, so this probably you are very familiar with. For chemical analysis, again, we can only model one species: chlorine decay, DBP growth, but we cannot model complicated reaction here. Like here I use just hydrocollosis, the chlorine with natural organic matter. Here KB is the bulk decay, basically. is what is lost basically in the bulk. And we know also the chlorine or disinfectant can be lost on the pipe wall, especially for older pipes or ferrous pipe. So, but we cannot put two species like national organic matter, chlorine in EPANET to model complicated reaction. Okay, now I can just show a simple, again, I go back to the net example. Then in the data option, quality, I choose chlorine, okay? Chlorine, there's some default relative diffusivity, this kind of, when you first use it, probably you don't need to change. In the reaction, it's kind of critical here because you define the reaction order, first order or zero order, right? So you give the K coefficient. So this is a single species reaction model, dCdt equal Kc. K is the reaction coefficient. So here I put a pretty high wall coefficient, wall decay, and relatively small bulk decay. If you want to know more information, you press F1. It will pop up the help file, and it will tell you what really all this coefficient means. Okay, then you click the source. You can see it's a reservoir, so we can have an initial quality. Basically, it's a reservoir quality, 1.0 milligram per liter. It's always 1.0 milligram per liter in the infinitely large reservoir. You can also put a source quality, even mass, like how many gram per minute you are going to inject here. So you can define different kind of source type. If I click here, let's see if we can have, okay. Oh no, it's reservoir. Okay, never mind. But in the user manual, you can see there is all kind of source type you can specify, booster, concentration, or mass injection. So I put one here, and you click some node, you can see the initial quality in the tank. Initial quality. I click the, yeah, initial quality in the tank also 0 or 1.0, but this will decay because it's in not water sources. Then I run, and you can see the chlorine concentration. I pick a node, I report, I graph chlorine. You can see the chlorine change in the system. The initial here is 0.5, so you can see with the 1.0 milligram per liter as the source, what the chlorine concentration will change over this 24-hour simulation period. One very useful information is here in the report called reaction. If you click reaction, you can see how much disinfectant or chlorine is lost, is consumed, I should say, in the system. In this one, you see half in the tank, almost 40% on the wall, and 10% about in the bulk. But remember, this model is highly hypothetical, so I really don't know if it's really telling the story. That's why I try to get some opinion from the experts in the audience. And you can see it also said how much kilogram per day. Yeah, it's right, totally almost 5, right? That's the disinfectant you are going to use for this very hypothetical model network and a very hypothetical reaction data. In reality, I know because we did some field work for bulk decay coefficient, we can have a relatively better idea because we can do bottle test in the treatment plant. We did that before. So basically, just recorded the sample chlorine concentration over time, like 1 day or 2 days, then try to see if first order or zero order decay matches, and to use some regression analysis to get the decay coefficient. But for pipe wall, I have no idea how to calibrate it. It's almost impossible. impossible. There are some papers talking about the relationship between roughness and the decay coefficient. There are some papers out there, but personally, I have no experience. So you can see I can change the reaction coefficient options. Reaction, I can remove the wall decay coefficient. Put 0, assume all pipes are very new and in perfect conditions. There are no global, no wall reaction on the pipe wall. Then you can rerun it. Of course, the chlorine loss will be less. Right? So if we click report reaction, we can see here we have how much loss in the tank, how much lost in the bulk water stay the same, 0 under the wall. So the total, of course, total chlorine consumption is reduced. All right, so I put this two graph here to show you again. When the wall decay coefficient is set pretty large, lots of chlorine or disinfectant was lost on the wall. And when you set to 0, it becomes 0. So I think in reality we can, what we can do is to using bottle test to get the bulk decay mechanism, and then we do some analysis in the system to see how much disinfectant was consumed in the system, then try to get an idea of how much disinfectant was lost on the pipe. That's just some random thoughts. Okay, to wrap up, EPANET application can examine both hydraulic and water quality issues for water distribution system. We know sometimes improving hydraulic reliability may hurt water quality, right? Because we just saw it. With very large tank, low over rate, the water age can be really a problem in the system. But if we have very small tank, and then hydraulic reliability may be compromised. As I showed at the beginning, it's not hard to build a very simple system model, right? One city can be even one junction with a fixed demand, but significant effort is needed to develop a good model. I have seen 100,000 pipes, 200,000 pipes, even 250,000 pipes model in terms of EPANET application. But when the model gets really complicated, it's harder to analyze, and it's harder to make it really represent the system. Lots of calibration, even field work, trace study are needed. Okay, I repeated the help links Robert just showed you guys, and I think, yeah, I'm done. Thank you.
All right, thank you, Feng. Thank you very much, and thank you for Rob too. A great presentation. Now, Rob, if you can throw your screen up or your cam up, I'll just ask questions for both of you, and one or two of you can pop in and answer them. So if you have more questions, put them in the question box. We probably have enough to go the next 15 minutes. But if you've got other questions, feel free to ask them. Okay, so you mentioned that it's chlorine decay can be modeled. Can chloramine decay be modeled?
Theoretically, yes. As long as you can have from bottle test, if we can have a curve that can and make you think the first order or zero order or even second order, this kind of single species model can mimic the reality well. Yes, of course you can do that. But if it's really complicated and the single species model makes single species model very hard to get accurate results, I think you shouldn't use it. But you can, of course, you just define a decay coefficient and run it just like a chlorine decay. But how accurate it will be is a question.
Gotcha. Okay. In terms of defining your system, are pipe length and diameter the most important things to input, or does pipe material matter?
I think you basically for the pipe you put in the diameter and the roughness. Roughness is quite important to define the hydraulics. But diameter you can also calibrate. There are lots of articles to calibrate diameters if you don't know accurately. But they are all more like static. The most dynamic is water demand. So if you don't get water demand correct, it's also you won't have good model unless even you have very good estimation of measurement of the pipe diameter and the roughness.
That's a good segue. So here's one about how do you determine your lengths of pipe within a system if you don't have great records?
This is an interesting question. So in reality, because I work with the industry for a long time, they first get GIS data from the local GIS office. Usually they have some data, and they need to do lots of engineering judgment. Sometimes they need to try and error to fit the field study. Yeah, if we say model is garbage in, garbage out, right? If you don't have really good input, it's very hard to progress. Yeah.
Okay, so that's somewhat leads to a question that Rob answered, I think, a little bit in the first talk. So what other types of maps, base maps and other maps can you apply to the EPANET to have some functionality in terms of benefiting the program? Rob, do you want to cover that again, or
Oh,
Feng?
okay. Sure, I can go to let me go here so I can get to my screen. Yeah, it's somewhat limited. Let me I need to open up EPANET again, I guess. Let me see here. Okay, so I guess we go to EPANET. There is a example network that I think we provide let me look at all the files here, backup files, all files. So no, it looks, yeah, so if we go to network 4, let's open up that. And then we can load a backup file. Are you folks seeing my screen?
Yeah.
EPANET, this is example network 4. And then we can go under backdrop and load the backdrop for this folder. Of course, this is what it goes to, of course, is what I accessed last. Let me browse down through here and go to the projects, because I got a complicated file structure here. I have to find where it downloads this stuff at. And here, this is PMP now, where there's all files, I guess is what I want. Why isn't it locating? Oh, that's a backup file. That's not a map file. I just remembered that.
Oh, okay.
So what, do we have any examples of loading a backdrop file? Feng, any examples? I don't think there is there?
I don't have. Yeah, we don't have.
So
Okay, but it's possible.
It's very limited, I guess. Back to what I was saying earlier, that was a backup file for where you want your data to go. That's a different situation. You load a backdrop here, and you're really limited to what you can load in terms of a bitmap, enhanced meta file. Is are two types that Windows enhanced meta file or bitmap is what you're able to do. If folks can see that screen. you know, if you want to work in another environment, you have to work like a GIS environment. You have to work outside of EPANET for that.
Oh, okay.
You
Okay,
know,
great.
yeah. Now, the other thing to point out, I don't think Feng or I touched on it, but the whole nature of this map and being able to see these, see the map is because the coordinates are in the IMP file, in the text file. If there are no coordinates in the file, you can still run it, the simulation. It just won't show up in the map. And I say that to point out that the simulation is really independent of map.
Yeah, yeah. Thank you for bringing this out. Yeah.
Okay, good. Okay, here's another question. You can't model DBPs at this point. Is there an ongoing effort within the GitHub program for people who are interested in trying to extend this to DBPs, or has that been is no one really thinking about that?
You can model DBP as a single species. Probably I didn't say that explicitly, because if for single species, like if we model it as a disinfectant, it's decay, right? So you have decay coefficient is negative, so it's consumed in system. If you model DBP, you can say I have a first order growth coefficient. You can model that. So roughly speaking, you can do that in EPA as long as in the reaction you give a positive reaction coefficient. But of course, you cannot model like the reaction between natural organic matter and the disinfectant to generate DBP. We had in EPA, and also I at that time I was a postdoc. We did some multi-species modeling, but we have the capability, and there is a EST paper about that. But we don't have user interface for multi-species reaction. It's in our research agenda, like with the recent 3-year, 4-year STRAP agenda to put multi-species capability more accessible. I put it this way. It's accessible in terms of engine if you can run in console mode or in DOS mode, or if you can program to call the library, you can do that to model complicated reactions. To bring it to end users, it's in our agenda for the next couple 2 or 3 years.
Okay, great. Do you need to? Here's a question. Do you need to enter in every fire hydrant into an EPA model to make it work well?
No, I wouldn't say so, right? Every fire hydrant is bit excessive, perhaps. That becomes a very detailed model that Feng was talking about earlier. With very complex models, you just struggle then to get everything right. The more complicated it is.
That's true. You know, utilities are moving usually from very scatterized model to all pipe model. So if we talk about all pipe model, it's like a 250,000, even 500,000 pipes. Then yeah, you can put hydrants as a node, but most of them won't have demand in daily time, right? So it's more, yeah, you can do that, but it will get very, very complicated. But of course, yeah, you can do that if you really want to have an extremely detailed analysis.
Okay, great. This might have been discussed, so I'm sorry if I'm asking a second time. So how do you get an ArcGIS file into usable form for use in EPANET?
Well, what you would want to do is you would want to, if you have your network model in ArcGIS, then what you would want to do is convert it or export it from ArcGIS to a text file that then you could run in EPANET. All right. If you have your model already in EPANET and you want to run or look at it in ArcGIS, then you need to find a software application that will allow you to export your map in EPANET, your network model with all the pipes, nodes, and everything, into a format that you can pull into ArcGIS. That would be either a shapefile or a JSON, GeoJSON file, are two examples. And if folks reach out to me or go to EPANET at EPANET@epa.gov, I can respond to that in more detail.
Okay, great. Okay, thanks, Rob. All right, let's see. Can it be simulated with VFD pumps? Can VFD pumps be utilized within EPANET?
It depends on what you're doing with what you want to do with the variable frequency drive pumps or variable speed pumps, essentially is what they're talking about there. And no, not in a way that they probably want to do. Again, email us on that and we can be more specific.
Okay, great. So this one's from Feng. There's been a number of questions. Well, and Rob, you could maybe chime in too. Just what's the basic pros and cons, or what's the basic differences between EPANET and other models that are out there commercially?
As far as I know, majority of the commercial software are based on EPANET. One exception I aware is wording for software. The InfoWorks WS is different. It's engine developed in UK, I think, long time ago. But Bentley's and WaterCAD, InfoWater, they all based on EPANET. Seeing that they definitely add a different kind of things, small things like the variable speed pump is a perfect example. InfoWater and Bentley, they both have a variable speed pump. So they based on their need, usually based on the customer feedback, they add different kind of features. But I should say 95% they are same in terms of engine. And of course, they have GIS capability. So if you have the budget, you can spend, so then you can get customer service. I know they are pretty responding. You can and they can troubleshooting your model. They can help you build your model. This is definitely a benefit. But of course, you pay the money, right? And I know some utility, even not small size, they use EPANET because they have in-house engineers. They like doing that. So yeah, it's basic. If you use EPANET, probably you don't have the GIS capability. That's a big, disadvantage, right? But you can really understand it. You have the source code. You can really understand how it is done. So that's, for me, for some engineer, is very intriguing, I think, to use some open source tool.
Okay, here's a question. Can you use to input information into EPANET? Can you use like a CSV file or digital evaluation model or some other type of model to help populate the data within EPANET instead of manually inserting them?
Yeah, you need to just you need to take it from like an Excel spreadsheet and then save it as a text file in the format that EPANET requires.
Yeah, because EPANET input file is a text file, so you can just open it. You can see it's a section by section. It's a text file, and EPANET user manual have detailed description of how the input file is organized. What's the format? Junction, pump, node, valve. So basically, one component is a line of text. So yeah, of course, even coordinates. So you can easily probably use some Python file to have your data to generate to convert your data into EPANET input file sections. Then you just assemble them together. It's a running model. You don't have to have even coordinates, as Robert said. You can run it, but you don't see anything on the GUI. It's empty, but you can still run the simulation.
Okay, great. So it's 3 o'clock, so I realize that some people have to leave on the top of the hour. So I'd like to just thank them, thank everybody for attending our workshop training session. The attendance was just fabulous today for both the ETDOT and the EPANET presentation. So thank you so much for attending our workshop. There are a few more questions, but I think you know, I think Rob and Feng are available for questions if you have questions about EPANET, and feel free to contact them. Their contact information is on those slides. If you have interest in the ETDOT models, contact myself or Johnathan Burkhardt, and our contact information is on that set of slides also. So thank you so much for attending our workshop training session, and please attend the rest of our small systems workshop. It starts tomorrow at 11 a.m. Eastern time, I believe, and then that's more of a typical workshop type of approach. There are a couple breakout groups for just state primacy agency officials to talk about issues with the EPA-ORD. So I'd encourage you to try to access as much of that material as you can from tomorrow through Thursday. So thank you so much for attending again, and thank you for our speakers, John and Feng and Robert. Excellent job covering these models. Hopefully we can do it again. If you have an interest in any of these models, or you think you can get involved in the GitHub applications and the open source applications of these models, feel free to contact Rob and Feng and John, and let's try to build this ability to do modeling across the nation. It can only help understand you know, what can be done then to better the drinking water system. So again, thank you so much. Thank you for our speakers, Rob and Feng, right now, and if John's still on, thank you so much, and I hope to see you tomorrow. Goodbye.
Thanks.
That concludes our webinar.
Thank you. Thank you.
You're welcome. Bye-bye.